Initiating virtual tour.
And we are live!
Actually, this is pre-recorded.
Hello there! You made it! Welcome to the virtual tour of the University of the Philippines, Cebu. I'm Annie, and I am a proud alumna of UP Cebu. And between just you and me, I had the best 4 years here in UP Cebu. I came from the College of Communication, Arts and Design, where we did not learn only the basics in journalism and other communication components, but they also taught us how to become relevant.
You only have one viewer.
My college is also home to the fabrication laboratory, where people meet and converge to use different equipment where they can fabricate things, stuff for the advancement of industrial and product design. All of this comes from the creativity of the Fine Arts program itself. Hey Sean, why don't you tell them more about the Fine Arts program?
The Fine Arts program itself, founded in 1975, is the pioneer formal school in the fine arts outside the national capital. The college is also the host to nearly half a century-old annual painting competition, Jose Hoya Awards, in honor of the famous national artist Jose Hoya, and from whom UP Cebu's Jose Hoya Gallery was named after.
As the campus of the premier university here in the Visayas, we have to be good. No, we have to be better, or even we have to be the best, not only in the humanities, but even in the sciences as well. Isn't that right, Sean?
That's right, Annie. In 2014, UP Cebu Senvi, or the Central Visayas Center for Environmental Informatics, came up with high-resolution maps using LiDAR technology. The use of this technology by UP Cebu Senvi provided government agencies with accurate data for more precise community flood risk assessment and management. This helped local government units make informed decisions based on data science and, in the process, maximizing their financial resource utilization. And in the case of the Naga Cebu landslide of 2018, UP Cebu Senvi's use of LiDAR technology allowed for one of the fastest search and retrieval operations in a disaster in the Visayas.
Helping the community through the sciences is very fulfilling. But we were not just exposed to that. We were also exposed to the social sciences, from political science to psychology, and all of these concepts helped shape our mindsets to become better citizens. In fact,
the College of Social Sciences articulates and addresses global challenges. The college offers comprehensive and appealing programs for high school, undergraduate, and graduate students. The Master of Education program is a non-thesis graduate program designed for graduates of the Bachelor of Elementary Education or Bachelor of Secondary Education who want to pursue their professional preparation through future studies in areas relevant to teacher education.
And of course, there were also budding business leaders in campus. They were the ones who had the nose for business but had the big heart to be of service.
Under the School of Management, students are not only taught to be decision makers, but the forerunners in marketing and finance. It also hones those interested in further studies of this field through its Masters in Business Administration program.
Today, I am now a practicing broadcast journalist, an opinion columnist, an entrepreneur, a teacher, a better person, really. All of this because of my training and experience at UP Cebu.
Nurtured to create, inspired to innovate, destined to serve. We at the University of the Philippines Cebu are driven by academic and operational excellence.
And that's it. Thank you so much for joining this virtual tour. I'm so happy you took part. Oh look, Sean, a lot of people are tuning in.
But the tour is over.
Well, we'll just do it again.
Ready when you are, Annie.
Reinitiate virtual tour.
Hello, everybody. Good afternoon. And today is our last leg of Click. And we have a very special session for today because we will be learning one of the major techniques in machine learning, and it is called manifold learning. What I'm seeing here, we have about 20 participants coming in. Thank you so much for being with us and attending, as well as participating later on in our question and answer portion. And I do hope you are very excited to be with us in this learning session. Before anything else, we would like to have our webinar etiquette. Miss Paula, kindly take the floor.
We will be recording the webinar for documentation, evaluation, and dissemination purposes. Note that by attending, you are permitting us to use any form of participation for such purposes. Mute your microphone during the session. We want to make sure that the speaker is audible to everyone. We may remove you from the Zoom if you do not comply with this request. Refrain from taking pictures or videos of other participants. You may be held accountable for data privacy violations if you post such photos and videos without consent. For questions and inquiries, you may utilize the Zoom Q&A feature. Questions will be addressed after the presentation. Don't forget to evaluate. The link to the evaluation form will be posted on the chat box at the end of the webinar. It will be accessible for 10 minutes only. Digital certificates will only be given to those who have successfully registered, participated, and answered the evaluation form.
All right. Thank you so much, Miss Paula. And please do note, make sure to evaluate later on after our webinar session. Now, of course, just like me, I think you are also very excited to know more about machine learning and this particular technique, manifold learning. For those who are interested, machine learning is just as important as anything else, especially now in our technologically advanced world. And machine learning teaches machines to learn from data and improve without being explicitly programmed. So today, we'll be learning one of the many techniques in machine learning, and this will be outlined as well as introduced to us by our speaker. And this particular session, just like the other three sessions that we have, is a partnership with the University of the Philippines Teaching and Learning Resource Center and the Department of Computer Science. Today is very special because we will be having the chairperson of the Department of Computer Science to be having a lecture or helping us learn more about this technique. Now, before anything else, I would like to call our coordinator, Professor Fernan Bernardes, to further introduce to us our speaker. Sir Nan?
Yes, thank you, Miss Jara. So, good afternoon, everyone, and welcome to this afternoon session. This event is still part of our continuing efforts to promote innovation and also research excellence in computer science and also in related fields. We are honored, by the way, one moment. Okay, there you go. We are honored to have with us Professor Daryl Prince M. Abellana as our esteemed educator and also our presenter later. He is also a researcher and also the current chairperson of the Department of Computer Science at the University of the Philippines, Cebu. With an impressive academic and also research portfolio, Professor Abellana has published over 31 research articles in peer-reviewed international journals with index in Scopus and also Web of Science. showcasing his significant contributions to the global scientific community. He is also currently the associate editor for the International Journal of Applied Industrial Engineering and an active member of prestigious organizations such as International Honor Society of Phi Kappa Phi and also Institute of Electrical and Electronics Engineering, or IEEE, the Association for Computing Machinery, or ACM, and the Mathematical Sciences Division of the National Research Council of the Philippines, or NRCP. Beyond his research, he has served as the technical session chair and also a program committee member for various index international conferences, further demonstrating his commitment to advancing the field. Professor Abellano's research interests include computational intelligence, machine learning, data mining, and also their applications. His work reflects a passion for harnessing these technologies to address complex challenges and drive innovation. Today, we have the privilege of hearing from him as he shares his expertise and also his insights in this topic. Please join me in giving a warm welcome to Professor Daryl Prince M. Abellana. A round of applause, please.
Hello, hello. Thank you for that introduction, Hernan. But I'm not really an expert on manifold learning, though. I've used it in some of my papers, but I think I'm still so far from being an expert in manifold learning. But I'm really honored to be here. Thank you for that, Hernan, for inviting me in this session. So I don't know. Can I start my presentation now?
Go ahead, sir.
Go ahead, sir.
All right. Sige. So let me share my screen. All right. So in this session, we're gonna tackle, or at least unlock from the title, unlocking the power of manifold learning, and it's going to be an introduction. But when I prepared this presentation, I think I kind of place a lot of information here. So I think we'll see lang no kung masulod ba siya sa 1 hour and 30 minutes kani siya nga mga slides. Daghan ko nabutang na parts of slides. So we're just gonna run through some of the areas that don't need a lot of emphasis, not to make sure that this fits our timeline. Okay, so manifold learning. Before we touch on manifold learning, it's important that we first contextualize which field manifold learning really comes from. So it comes from a broader field called artificial intelligence, which I believe many of us, if not all of us, are familiar with, especially we have ChatGPT, we have other LLMs like Gemini phones, AI in action like Apple Intelligence, if you're using the latest mga Apple iOS devices, and many more. So this AI, or artificial intelligence, is really a field it's a field in computer science, but it's do in computer science. And so, for example, we have computer vision. This field, for example, allows computers to understand things that can be things that humans can see, for example. So before we deal into each of these, let me just briefly describe what AI really means. So in layman's term, we think about artificial intelligence as a way, or meaning of as the study of algorithms that mimic human intelligence. So meaning to say how humans reason, how humans perceive the environment, for example, and how humans make decisions on some problems, or even how humans solve problems. And this process of mimicking this human intelligence, when we solve problems that require human-like intelligence, for example, can be partitioned into several parts. So we have here computer vision, NLP, computational intelligence, expert systems, machine learning, robotics, and many others. These are just some of the primary branches, or the most common branches that are studied in AI. So computer vision, for example, mimics how, as mentioned before, mimics how humans perceive the environment through vision. So for example, through images, through videos. We also have natural language processing, which basically gives the computers the capability to understand natural language like speech, for example, texts, for example. Robotics, of course, when we talk about AI, I think what comes to mind are really robots. So robotics would give these computers the ability to interact through physical actions, with its environment, like drones, for example, and many other devices that would do some physical activities. So and expert systems, which basically mimics how humans, how experts solve a problem, how experts decide on something. And we also have another one, which is computational intelligence, and we can consider this as more like the branch of AI that tackles the problems which have an inherent uncertainty. So things that you cannot explicitly solve. So for example, in a search problem, if you want an exact solution to it, you might use an optimization algorithm, a combinatorial optimization algorithm, to get from point A to point B using several paths. But here in computational intelligence, it does that by allowing some form of uncertainty. So some form of suboptimality in that case. So for example, I might be using an algorithm that mimics how an ant moves from a certain path, and that path might not be optimal in that case, but it solves it because it's practical, and because sometimes problems cannot really be exactly solved, so we allow for solutions that are approximate in a way. So things like fuzzy logic come into this part here. Artificial immune systems, evolutionary algorithms like genetic algorithms, if you've heard of them, and many more. And the last one that I mentioned here is machine learning, because this will be the topic that we'll be dealing with. Is a branch of AI that lets computers learn from data. So we're gonna define what learning means, but it in layman's term, this means that we, we are giving the computers the ability to, for example, understand this could be encoded in the form of historical data, for example, or for example, previous mistakes. When you interact with an environment, you might have an experience that doing this might not be a good idea. So using machine learning, we can encode that experience now to the computers. So we're gonna define that later, but for now, just think of ML as basically the branch of AI that allows computers to learn from experience. So learn from data in that sense. And I think in the introduction a while ago, it was mentioned that machine learning is the ability to computers without being to learn from data without being explicitly programmed. That's also one of the most popular definitions of ML. But in a nutshell, it really just means that we're giving the computers the ability to learn from experience. Okay, so it is undeniable that ML, or machine learning. So I'm not gonna mention ML because manifold learning could also be termed ML. So to avoid the ambiguity there. So I'm just gonna explicitly say machine learning has really become one of the most important areas of artificial intelligence in the 21st century. So things like, for example, detecting objects in this image, or segmenting this image into different parts, and even, for example, solving optimization problems like this one here is genetic algorithm. It mimics the process of how, for example, genes evolve to solve a particular optimization problem. And even um, knowledge, understanding of many more. So areas. We have so the first one is called supervised learning. So the input for a supervised learning algorithm is a data set which has some features. So we're going to define what features are later, and a certain label. So for example, if I want to teach my computer that something is a cat, then my data set or my features X would involve the features or distinguishing features of a cat. For example, the face shape of a cat, the ears of a cat, if there are the whiskers of the cat, for example. And if I want to tell the computer that this one is also a dog, then I'm also gonna feed it some information that allows us to distinguish what a dog is. So this distinguishing features of a dog. So its inputs then are data with labels. Okay, I'm gonna for now. No, I'm not gonna introduce vectors for now. So I'm not gonna formalize it for now. So, but think of data inputs as basically just you can think of them as maybe variables that allow you to determine what your prediction is or what something is. So for example, if you're familiar with regression, you have your features there, your independent variables, and then given this independent variable, what would be the outcome or something like that. Or here, we call the target as the label. So that could be a cat or a dog or whatever that label is. And then the features are the quote unquote features that from the word itself, feature, no, are the things that allow you to distinguish between what something is. And we call that paradigm the supervised learning approach, because we're supervising the computer know what something is. So we're explicitly telling the machine what a dog is, what a cat is. So if you see these features, you know that this is a cat. If you see these features, you know that it's a dog, and it's supervised learning. Okay, so there are two areas of two types of tasks. Now for supervised learning, we have classification, where we are predicting categorical objects. So for example, dog or cat. So things that you can count, for example. But there's also another field called regression, where we are predicting continuous values. Like for example, the height of someone, the weight of someone, the price of the market, things like that. So things that can be expressed as continuous attributes. And finally, what we do here is that we want to learn a certain mapping for that. So that would be the output. No? So which tells us that if I'm given this particular features, should my machine predict that this is a dog or this is a cat? Another area is unsupervised learning. So from the word itself, unsupervised, I am not telling my computer, I'm not telling the algorithm what a cat or a dog is. So what I'm going to do is just feed it with a lot of images or a lot of features, and then decide for itself which ones could be category A or category B. So for example, if you feed it with the images of birds and cats, then it might be able to distinguish between a bird and a cat on the basis of the wing, of the presence of wings, for example, or the beak, for example. So if I know that these certain features are present, my algorithm might say that this is a bird and this is a cat. But again, since it's unsupervised, it doesn't really know what the actual names of these categories are. It just knows that there's a category A that has these certain features. There's another category that has these certain features. So because it's unsupervised. Okay. And the other branch of ML is reinforcement learning. So here we are learning from rewards. If we all remember, when we were toddlers, for example, our parents did not teach us how to walk, right? So we learned how to walk by making mistakes. For example, kung Madam Agka, for example, you know that that's not the right way to walk. If, for example, you would stumble, you would see an object and then you continue walking, that you would stumble, you know that you should not go through that obstacle because you might stumble. So reinforcement learning, the paradigm for reinforcement learning is allowing computers to learn through rewards and penalties. So algorithms, I'm kind of switching between the two terms, but an algorithm, it allows the algorithms to learn about a certain task through rewards and penalties. So for example, if you don't want your algorithm or your robot, for example, to touch or to burn to touch a fire, so of course you might want to let it experience what it feels, what burning feels like. So if it knows that burning is kind of not rewarding because it's penalizing, then you wouldn't want to touch a fire again, or something like that. So you're not telling the computer what a dog is, what a cat is, or you're not even making the computer distinguish between the categories of an object based on features. What you're really doing is that for a series of rewards and penalties, your computer learns on its own what is good and what is bad, or things like that. So of course, now I'm not talking about morality here, but good and bad. I'm just saying that what is rewarding or not rewarding. Okay, so these are the different paradigms for machine learning. And the part that we will be explicitly dealing with is, I forgot to mention that this also has two parts. One, to distinguish between various categories using the features, and the other one is dimensionality reduction, where we want to reduce a high dimensional data, for example, or not necessarily high dimensional, but a data set with a lot of features, and then we want to project it to a lower dimensional space so that we can visualize, for example. So this might be useful in cases where, let's say we have 100 independent variables, and we want to visualize these 100 independent variables. Of course, our intuition, our limitations as humans is that we can only visualize that in 3D. And if we want to some kind of extend that in one dimension, that we might want to view a 3D shape changing over time to at least account for the fourth dimension. But at 100 dimensions, I think it's really impossible, and it's counterproductive to do so. But dimensionality reduction would allow us to leverage the patterns in that high dimensional space and project the dimensional space that basically represents what we're doing at the higher dimensional space. So I think a straightforward intuition to this is a contour plot, for example. So if you remember your mathematics in college or in high school, your calculus, for example, is that if we have a surface, for example, we can view it in a lower dimensional contour plot, which only has which is 2D, for example, but we can still visualize what happens if we move around this area. Okay, so yeah, so this would be more of like a graph of what these areas of machine learnings are. So again, as mentioned, we have supervised learning, and this can be divided into two parts: classification and reinforcement learning. So far, now before we dive into what these algorithms do, let's try to have a brief overview about the current state in the literature. And we can see here that most of the papers in the literature, at least up to 2020, this review is kind of outdated. I just pulled it up. So we can really see that most of the shares here in the research, at least in this field, is on classification. And I think most of this really comes from application areas, like, for example, applications in engineering, in healthcare, and other domains. So I think it's kind of natural that we have classification as having this major share, because most of the problems probably that we're dealing with are things that already have labels. So I want to have an algorithm that determines whether this fruit, for example, has this disease or not, or, for example, predicting whether something is a 1 or a 0, etc. So there's really very little share about these other areas, like especially dimensionality reduction. So it's not even included here. It's not as much as the others, but there's still progress in that area. So these are just some of the examples for classification algorithms. So of course, no, spam filtering for supervised learning. So spam filtering. So if you've noticed that your email automatically detects whether an email is a spam or not, then that uses a classifier. So I think one of the popular examples of that is using an algorithm called naive Bayes. So it determines whether the contents of your email could be are more indicative of a spam or not. So they would put it in your spam folder. Face recognition, for example, is one, and probably in banks, predicting whether a certain person would predicting the credit score of a certain person. Okay, so in this case, it's an ordinal. It's expressed in ordinal categories. So it could still be under the. There are papers that would consider this as a classification algorithm if we try to disregard the order of these scores, but there are also some that would consider it under regression. So it's kind of like in the boundary of the two. Okay, so with more applications made to drive scientific discovery, business intelligence, and other important real-world applications, data sets tend to be high dimensional, though. So the thing is, it's good that we have these classifiers, we have these algorithms to deal with these problems that we're facing, like face recognition, for example. But it turns out that a lot of these data sets, at least in important applications in the real world, a lot of them tend to be high dimensional. So when we say high dimensional, we mean that we have a lot of features. Although there is a technical term for high dimensionality, when we say something is high dimensional, we really mean that the number of features or independent variables are greater than the number of observations. But we're not gonna we're gonna kind of relax that term a little bit, just to avoid just for the sake of our discussion. Okay, sometimes I would just call them high dimensional, but really we have more samples compared to the dimensionality. But just think of it as having a lot of features. So I think a better way of saying it is that a lot of data sets that we have, at least in the real world, tend to have a lot of dimensions or a lot of features. So for example, this one here is the MNIST handwritten digits data set. So this is a data set that basically collects images of how people write the digits from 0 to 9. So some people might write 9 in a very nice way, but there are people who don't have that dili inakanindot og penmanship. So like me, for example, my 9 might be a little bit slanted, or it might not even be. Sometimes it might even look like a 4. So the thing with these data set is that at least if we don't use mga feature extractors like convolutions, I'm not gonna talk about that for now, is that the features of this image are the pixels themselves. So if you have an 8x8 image, so you would have 64 pixels, and let's just imagine that the features there would be 64. So if we want to visualize how these different digits cluster with one another, for example, or how they're contextually related to one another, we might want to visualize them in a two-dimensional space. But again, the problem is you have 64 pixels. So one of the ways to do that is to project the data into a lower dimensional manifold, into a lower dimensional space, which we will talk about later. And you have this. So kanisha iyahang spreads. For example, these orange ones here are the number 6. These one here, you could consider them as the group of the number 6, and then you have some groups of the number 2s, etc. So another one here is a high dimensional. Again, it's a time series with a lot of features, and I think if I remember correctly, this is modeling the stock price or something. I forgot, but this is a time series data with a lot of features. So imagine, for example, that you're keeping track of, let's say, for example, 100 cryptocurrencies, and each of these cryptocurrency would have a price daily, right? Would have a daily price, and if you're keeping track of that over time, then you would have a time series with 100 features, and these features represent the cryptocurrencies, and then they also evolve over time. And because the temporal relationship is important here, we also want to keep track its previous values, so it becomes a very large data set. Okay, so the thing with these high dimensional data, this data sets with large dimensionality. So I want to avoid saying high dimensional data because the dimensionality reduction algorithms are applicable not just to high dimensional data. So large data, so I'm just going to say large data sets, but sometimes I forget saying that. So the thing with these large data sets is that they exhibit something called the curse of dimensionality. And here, we're going to try to formalize things a little bit. So for those who are not so comfortable with the formalism here, so we're going to give some intuition. I'm going to give some intuition every so often. So for those who are not so into the math here. So our assumption here before we go into the curse of dimensionality is we assume that we're going to use something called an L2 norm, or the Euclidean distance, or basically just if you have 2 points, it's basically just a straight line distance between them. If you remember your trigonometry, just like if you have a triangle, for example, then it's like the hypotenuse. If you draw a triangle between these 2 points or these 2 persons, then it's just the hypotenuse. It's the straight line distance between them. And it's expressed using this formula. So we represent points in the space as vectors. So you have, and the components of the vectors are u1, u2 to up. So for example, if you have a 2-dimensional grid, then your vector would just have a u1 and a u2. u1 representing the x-axis, u2 would be representing the y-axis. But since we want to generalize this to like p dimensions, because again, we're dealing with large dimensions here, which is why we need to use dimensionality reduction algorithms, then we represent that with a vector from u1 to UP. So the components are U1, U2 until UP. And then another vector V here, which is also p-dimensional. And to compute the Euclidean distance between them, we just use this formula here. We take the sum of the square differences between the components. So for example, if we start with U1, so that's just U1 minus V1, then you square that, and then you add U2 minus V2, you square that, etc., etc. And then when once you're done summing them up, you take the square root. Okay, so it's important that we have an assumed norm here, because I'm going to show something later, at least not to not really prove it, but at least to get us very close to understanding what the curse of dimensionality really implies. So imagine that we have a one-dimensional data here. So meaning to say we only have U1 and V1, or you can consider this as just an x-axis. But because I want to generalize it later, I'm just going to call this axis x sub 1. Okay, so that would be the y-axis, or x sub 2. But because I want to generalize, I'm just going to put subscripts here. So this is just one-dimensional. There is no dimension at this vertical axis, just the horizontal axis. Now, if I want to embed this in the space here, so this would be U1. This would be the position of the point U, and it only has one component because it's one-dimensional. And let's say that it's resided on a point U1. So if you want to assign real numbers here, you can say that this might be 1.1, and then V1 might be somewhere 2.2. But I want to be arbitrary here so that we can generalize. So U resides on the point U1, but you can think of any numbers here. So let's say, for example, 2, and this could be 3, and then you can take the difference between them. And to compute the distance here, using our assumption, using our assumed norm, which is the Euclidean distance, we simply take the square root of U1 minus V1 squared, and then we take the square root of that. And that's just equivalent to the absolute value of their difference, right? So whether I'm differencing, so if U1 here is 1 and V1 is 3, then this distance would just be 2, right? It makes sense that we just take the difference between them. Okay, so what if I add another dimension here? So let's call that dimension U sub 2. Or because this is 2D, for those who are not so comfortable with that, you can think of this as the x axis and then the y axis. So if I add another dimension here, x2, that would mean the point can only move in these horizontal directions. It can be placed here, it can be placed here. But here, since I now have a vertical axis, so my point can also move upwards or downwards and left or right. So if I now say that the second dimension of my U is at U sub 2, and for V, that would be V sub 2, then this means that this point here would actually move in space as well. So this would now be its new visualization. So this would be the y-axis of U, or the x sub 2 axis of that, which we call U sub 2, to generalize easier later. And then V would now be at V2. So now the coordinates of U are now U1, U2, and the coordinates of V will now be V1 and V2. That seems pretty natural, I think. So if I want to compute the distance between them, I still compute the straight line distance between them. So that would just be the Euclidean distance of U1 minus V1, just according to our formula, and U2 minus U1 minus V1 squared plus U2 minus V sub 2 squared, and then I take the square root of that. Okay, so that would be the distance between them. We're not going to quantify that specifically because we haven't assigned a value here. But if you want to make that more precise, so you want to assign some value here, you can say that if this is 1 and this is 3 here, and this is 1 and this is 2, then you just replace these variables with specific values, and then evaluate the Euclidean distance. Okay, now let's add another dimension. So this one, the previous dimension was just 2D. So you just have the x and the y axis, or the x1 and the x2 axis. But here I'm adding another dimension. So you can think of adding a z dimension. So we're now moving from a 2-dimensional space to a 3-dimensional space. So here I'm adding a z axis, but I'm calling this x sub 3. So naitabo is that kani siya nga plane is actually more like, if it's facing you, mura na siya gipahigda, so that it's now lying on this flat surface, and then there is now a z-axis or an x3 axis that accounts for the height of that particular plane, for example, of that particular solid or surface lying on that 2D space. So what happens is that if I now assign a coordinate to it, it will also move, right? So it moves because it now accounts for this U3 and V3. Now, the thing is, it wouldn't move if we just assign zeros here, but that would be trivial because if I'm just assigning zeros in this new space, then it's basically just the same as not adding that space. So we wouldn't give us more information. So what we're really assuming here is that we're adding some values that are not zero. So at least zero everywhere, but you could add, for example, kung U3 is not zero, but V3 could be zero. So I think that would be okay. But if all of the entries in the rows here would just be zero for X3, then that wouldn't be useful. So we're not gonna do that. So when we add this U3 and V3, what happens is that it moves. So it's still lying at U2 and U1, but it changes here because na naman mag-slanted at perception. But the thing is, what's just happening is that I'm just bringing it up to account for this additional dimension. Okay, so if I want to compute the distance between them, I still use the same formula. I still get the straight line distance between them, but what happens is that this distance changes as well. So this is now different from the previous one because here, it's just the distance between them if they're lying on that flat table, for example. But here, we're now moving it up because they now have this X3 dimension. So their distance might also change. And the distance is now this one. That's U1 minus V1 squared plus U2 minus V2 squared plus U3 minus V3 squared, as opposed to this one, which is just U1 minus V1 squared plus U2 minus V2 squared. Okay, so I hope that you kind of get the pattern here. I hope I'm not so fast. But if I'm gonna ask a question, did you notice something with respect to, for example, some of the quantities here, like the distance, as we add more dimensions? I don't know if I can ask the audience, but is it okay to, Sir Nan, to ask you or
we can
the
have
reactor?
them chat there.
All right. So
May-
before I proceed, Miss, maybe I'd like to ask the audience what they've noticed as we kept on adding the dimensionality, at least with respect to the distance. What do you think is happening with the distance? Is it increasing? Is it decreasing? Does it remain the same?
For our participants, you may put your answers in our chat box. Thank you.
Okay. Sige. So
Sir, may I give my reaction first?
yeah. Go ahead, Miss.
I'm sensing that the more dimensionality you are putting in, I mean, the more dimension you put in, the more sparse the points are. So it's increasing in distance. And
Yes.
looking at it, I figured out that this actually happened in one of my theses before.
Okay, that's good.
We were looking at audios of bird sounds, and then the more dimensions or features we add to it, the lesser patterns we get. So, or trends that we get. So the more spacious or the more distance, it would the change would be more distance.
Yes, that's a very good insight, Miss. So actually, that's correct, no? Medyo disadvantage ng ubang audience because she actually experienced that in her thesis. So, but yes, that's a very good insight. Fernand also mentioned increasing, which is also correct. So that's actually right. No, that's right. The distance either remains the same or increasing. So, but it doesn't decrease. So I'm going to talk about the distance remaining the same in a few slides, but in general, it's really increasing. And in fact, if you look at this, if we look at this from a mathematical perspective, if we set j equal to 1, meaning say we are at the first dimension, so d1, then our distance, the distance between u and v would just be the absolute value of u1 and v1. But if we increase this to 2 dimensions, then we would have u1 minus v1 squared plus u2 minus v2 squared. If that's in d3, this term keeps on increasing, right? So that would be u1 minus v1 squared plus u2 minus v2 squared plus u3 minus v3 squared. And in fact, if we generalize to p dimensions, we would have this distance here, which is just the It's the sum from j equals 1 to p of u sub j minus vj squared. And it's not difficult to see that this relationship holds. No, kani siya nga particular relationship. We know that this u1 minus v1, we know that this distance of the two dimensions should be at least as large as u1 minus v1, and so on and so forth. So in other words, if we represent this as just a distance, d1, we know that d sub b is at least as large as d sub b minus 1, so on and so forth. And d sub 3 is at least as large as d sub 2, is at least as large as d sub 1. And in fact, if we assume that these values here, no, so on values that there are not constant values, so for example, not zeros or not ones, we know that this would be really increasing, right? So for example, if I know, so the only trivial case where the distances do not change is when the added features have constant entries. Kung puro ra siya 0 or puro ra siya 1, so meaning to say they're all the same, then it would not change, because what happens is that you would have u1 minus v1 squared plus c minus c squared. They will all just be 0. But again, as mentioned, this is a trivial case, because why would I add a column in my data set that doesn't really give me additional information? So if they are just constants, like for example, all ones, all zeros, all any other constant value, any other real number there, then it wouldn't be adding information to my data. So because that is a trivial case, what really happens is that if I add additional columns, it would necessarily increase the distances among your objects. And as mentioned by Ms. Ganina, no, yung giingon kay, they notice that the data set actually becomes sparse. So we need to say that the points become farther and farther apart. No, it's farther, not further. Sorry, farther and farther apart from one another. And in fact, empirical evidence suggests that if you kind of, let me just draw this. But disclaimer lang, hindi ko may drawing. So, pasensya akong drawing. So, let's say, for example, that we have this 3D. Okay. So, let's say, for example, that the actual volume that we want to learn about our data points would lie in this sphere. Just imagine that this is a sphere. Okay, but I'm not really good at drawing. So, anyway. And then there's a box here. So, we call this box as the shell of the space, and then this sphere is the supposed volume that we wanted to learn. Now, what happens is we keep on adding dimensions is that our data points would move farther and farther apart, so they would actually tend towards the shell of the space. And the problem there is that distances become so large, and when they become so large, let me just erase this for now. Okay. So for now, we're just going to say that we know that this distance becomes so large. But the question is, why is this increasing distance a problem? Ms. mentioned that about the sparsity of the data, it becomes so sparse. So in fact, that's the next one that I'm going to talk about. So what happens is we increase the dimension. Increasing dimension leads to, sorry about the typo, to data becoming farther apart from each other, resulting into a sparse data set. So when we say sparse data set, it's just a data set that has if you place an array of that, there might be a lot of entries that are zeros or not really important entries. So meaning to say, grabe siya ka-sparse. No, they're not dense. So that's what sparseness means. So in this case, they would become farther and farther apart because they're so far from each other. It would be difficult to create, for example, clusters of these points because they're now farther apart from one another. So for example, data points that are closer in the one-dimensional space may become more distant in 20 dimensions. And this is important because I think that there are a lot of times when we think that when we add a feature to our data set that we're actually doing doing favor for our algorithm because, for example, okay, so mag-add lang ko ng feature para mas maka-learn akong algorithm. But the thing is, it might actually it would actually have some bad implications to the algorithm if you do that blindly. So when we add features to our data set, we really have to think about that in a more systematic manner, not just doing it arbitrarily because, again, it might make your data more sparse. And sparsity is just one, but this cascades into other problems. And we call that one the concentration of distance problem. So formally speaking, that's when if we have a data set X here, which is just a set of the observation vectors, so X1, X2 to Xn, meaning I would have n p dimensional vectors here. So you can just think of of a data set with p columns and then n rows. So if you want to visualize it that way. So we let this be the set of n data points from the p-dimensional Euclidean space. So if we let q, which is also p-dimensional, be an arbitrary but fixed query points, I think one way of visualizing that is if you have this grid here. Okay, so, and then there would be some points here. Q would be one of those points. Okay, and we call that Q. So there could be other points here. There could be a point that's near to this Q. There could be a point that's far from this Q. And when we talk about any specific point in that particular space, now the point that we're referring to or that we want to measure, for example, we call that one, that's Q, that's an arbitrary fixed query point, a point that I want to query about. And if we want to consider, and let's also consider a distance function. We'll use the Euclidean distance because we're used to this in our example. What happens is that if I now assign two vectors here, 2 points in this space, so I call x to the negative the point that is nearest to my query. So let me just color that, let's say red. So let's say, for example, that this point here is the point that is nearest to my query point Q. So I call that x minus. So mathematically, that's just the argmin of the distance of xi to Q. So we need to say you evaluate all of these xi's here, all of these points. So can sila tayo na points din here. So this point, this point, this point, and then you assign to x1 the point that is closest to my query point. So in this case, this would be my x to the negative because it's the closest to my query point Q. And I assign to x plus the point that is also farthest. And I think visually, it might be either this one or this one. So let's just say it's this one. No, plus. Let's just say that it's that one. So we call this one x plus. Okay. And we call this red one here as the x minus because it's the closest to Q. Okay, so what scholars have observed is that if we measure the distance of these data points as we keep on increasing the dimensions, something really peculiar happens. Now, wait on, let me just erase this first. Erase that so that it doesn't. Okay. All right. So what happens is that as the dimension of my data set increases or approaches infinity, so it becomes very large, one finds that the distance of Q with respect to the nearest neighbor and the distance of Q with the farthest neighbor, they're actually approximately the same. So that's what they've observed in the literature. If we keep on increasing the dimensionality here, these two would actually tend to approximate one another. In fact, they become very, very close to one another. And in fact, since this the distance of Q x to the negative, in other words, the distance of the nearest point to the query point is less than the distance of the query point to any other point, less than or equal to that. And this is also less than or equal to the distance of the query point to the farthest point. Well, this means that all distances to Q begin to concentrate and are confined to a small domain. So this is a result from the paper of Kumari and Jayaram, I think, how do you pronounce that, 2016. But there are actually more papers, but I found their paper nice because they also did some theoretical guarantees here. So if you want to read about the manuscript, you can actually go to this paper. So what they've observed is that here, the dimension is just, M here is the dimension. So if we have 20 dimensions, we can see that the distance of, wala nakabutang ang legend here, but this is just the distance to the farthest point, the distance to the nearest point, and then any other point. So the red. So what happens is that they actually tend to become closer and closer to one another. If I increase this to 100, we can see that the band between them is actually getting closer. It's getting smaller. And if I do that for 1,000 dimensions, that will become even smaller. The thing is, Wanashagi progress more than that because probably it's gonna take so much time to simulate this. But there's also another paper that simulated this behavior using various probability distributions. So I think sa Kanisha, they assumed a uniform distribution and possibly other distributions. I missed that out. But there is also another paper that really tested this behavior for various randomly generated data points with different distributions. So one was using normal distribution, another was using the uniform distribution, other distributions. And what happened is that this behavior is really not just for a certain distribution, but this occurs to any other distributions that they've considered. And of course, the distances that are drawn for the Minkowski distance, meaning ito mga LP distances, Manhattan, Euclidean, and the supremum distance. So I think wala including other distances, but kato lang distance you consider nila to. But the thing is, it's not just, so you can't say that this is just because it's Euclidean, using the Euclidean distance, or that it's because it's using that certain distribution. The thing is, they found that this is really, this happens, no, even if you use another norm or if you use another distribution. Okay, so in other words, what we can say with this concentration of distance is that all the points in X are almost at the same distance to Q as you keep on increasing the dimensions. So thus the distances become less discriminative. So the problem with this is that if they're very far, the distances become farther apart from one another, and then these distances also become almost the same. So mura siya, in a way, they're evenly spread out na kung ana ka, same na ilahang distances with one another. The algorithms would find it difficult to discriminate between the various classes. So especially if you're using algorithms like K and N, which use distance, but scholars have also found that this is not only limited to algorithms that use distances. So even algorithms that do not use distances also find that a problem as or an issue. So as a pseudo solution, what if we add more data points so that the feature space becomes less sparse? So that's one of the quote unquote solution. I will see that this also leads to another problem. So one problem is that they become so far away from each other. What if we make sure that for every point, there are also other points in between them so that the distance is no longer that large between them? So let's say, what I'm saying is that if we consider this one-dimensional grid, and so initially, kung mo distance between, duha lang sila, mo distance between them, what we do is that we make sure to fill other points here as well. And each of them would have a certain coverage. So kung na ako'y point din here, then I know that the nearest neighbor would automatically be this one. And if I have another point here, then it would be this one. So essentially, we are trying to resolve that problem. But notice that we started with 4 points here. Okay, but if I increase the dimension to 2D, I would now need 16 points to make sure that that coverage is still maintained. So I'm just using a circle here, but probably it's not to demonstrate what coverage is, but probably it's not the best now. Shape to do that. We're really talking about neighborhoods here. This is just for visualization purposes. So kung naa din probably dapat mag-overlap siguro sila. But anyway, this is just for visualization. But the point is that if we keep on increasing this dimension, we are actually also increasing the number of points, right? So we now have 16 in this case. I would now need 16 points to make sure that that problem doesn't occur. And if I add another dimension in 3D, now it becomes so cluttered. Forgive my drawing, but overlap na sila. Some of them might not really be, but I just basically overlaid them. But here, we would now need 64 points to make sure that that coverage is still maintained. Now, the thing is, let's try to wrap it up. At D equals 1, we only need 4 data points to get a good coverage of the 1D space. But at 2, we need 16, or that's actually 4 squared, right? That's 4 to the power of 2. At D equals 3, that's 4 to the power of 3, or 64. Now, it follows that if we keep on increasing this dimension, we would now need 4 to the P data points to maintain that neighborhood. Okay, so in other words, if we need B data points to fill our 1D space, we would need B to the P data points to fill a P-dimensional hypercube. So thus, the number of data points grows exponentially with respect to the number of features. So in computer science, when we see an exponential growth, then usually that's a problem. In fact, many times, if we're talking about the running time of an algorithm, that would be a problem. If we talk about the memory or the space that an algorithm requires, that would be a problem. And in this case here, we are needing exponential number of data points just to learn. And now this leads to something called the curse of dimensionality, which says that as the number of features or dimensions grows, the amount of data we need to generalize accurately grows exponentially. So the point is that if we want to generalize accurately here, we need to make sure that when I have a data point, it has a nearest neighbor. Na siya way to determine unsa akong class. No? So, and if we want to do that, we really need to fill the entire space with with these points. And the reason why this doesn't apply only to algorithms that utilize distances is because algorithms in machine learning need coverage to learn or to be able to determine that, or to make predictions, for example, or to generalize to unseen data. We need to cover that space. No, we need, essentially what we're doing is we're learning a mapping that approximates the true distribution of the data. And to do that, we need to put some points that have that coverage. So if we are going to stick with that assumption, now that we make sure that we fill those space with neighbors, then we would need an exponential number of data points to really learn. Now, the problems here is that it becomes computationally expensive to train classifiers, because if you have these features, I would now need this amount of data to learn or to generalize accurately. But we're going to talk about what that means later. So interpreting models become more challenging because you now have a lot of parameters to learn. You now have a lot of features. And of course, no, generalization becomes difficult because imagine you have B to the P data points that you need there. So high dimensionality also leads to prevalence of noisy, irrelevant, and redundant data, which undermine the performance of classifiers. And these problems are collectively known as the curse of dimensionality. Now, the thing is all hope lost? No? When I first read about that back in my graduate degree days, no, during my master's, my thesis was on feature selection is a different type of dimensionality reduction algorithm. But when I read about the curse of dimensionality, I kind of like had a very, what I go on a mood. Okay, so it's all hope lost here. Is there still a reason for developing these algorithms when in fact, no, it's a very fundamental issue that we really want to generate accurately? We will need that much data points. So should we just give up? The thing is, there might be a way to counter a curse, no? And in traditional folklore, if someone would ask you when I curse, what's the best way for countering that curse? Age-old wisdom would say that the way to counter a curse is through a blessing, right? And that is also the case here for machine learning. Buyag daw. Yeah, in traditional folklore, that's what we do. So fairy tales, for example, manailang buhatan to counter a curse or to break a spell, for example. But fortunately here in machine learning, we have this thing called the blessing of non-uniformity. Now remember that in my assumption here, qualitative assumption, I was assuming that the data points are uniformly spaced or uniformly distributed, right? So in reality, that might not really be the case. The thing with real data sets is that although some of them might be have large dimensions or have many dimensions, they might not really be distributed in a uniform manner. So for example, images. If you have an image with 64 pixels, 64 is a lot. And if you have a higher resolution image, you would have a lot of pixels. But the features in the image, for example, the nose of a person in that image, the eyes of the person in the image are actually concentrated in a certain region. So meaning to say the context or the contextual features here are not really uniformly spread, because if it's uniformly distributed, it would just look like a random image, right? A random noise. But the thing is, in reality, these images are not that, they're not really uniform, they're non-uniform. So this blessing of non-uniformity is, it partly counteracts this curse, but not entirely. It just partly counteracts that, just gives us some glimmer of hope that there is still a reason to do machine learning. Because in most applications, again, the examples are not uniformly spread throughout the instance space. So, but they might be concentrated on or near lower dimensional manifold, which we will be talking in a few now. So this actually motivates the reason to do something called dimensionality reduction, which we can separate into many parts as well. So in the current literature, scholars have paid attention. So balikan na natin, no? The reason why we're doing dimensionality reduction is that we think that through the blessing of non-uniformity, the data points are not really uniformly distributed or spread out throughout that high dimensional space, but they actually lie on a lower dimensional manifold, which we want to learn. And what we want to do is to, instead of learning that high dimensional space, we want to learn what that lower dimensional manifold is, the form of the structure of that lower dimensional manifold, because we might be able to find some contextual relationship there. So in the current literature, scholars have paid attention into developing algorithms for reducing dimensionality. So we can generally divide them into two parts: feature projection and feature selection. So these two methods are different in how the reduction process is carried out. So if you talk about, so I'll just briefly talk about them na lang, because so that we can go to the manifold learning. But just think of it this way: feature projection basically what it does is, if I have this data set here, okay, so naka data set din here, and then it has these columns, so dot, 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 and then, so this will be the first dimension, second, third, until P. Okay, what feature selection does is that these dimensions here, these features actually constitute a set. So if I call that set F to be the set of my feature until FP, F sub P, what I want to do with feature selection is find an algorithm G, okay, to this feature set. Well, to the same feature set, but with a different ordering. So I think you can do it that way. So pati kay kumusuwat din. Lisod kaya siya. I would like to use my iPad, but it will take time to set up. So dito na lang siguro. So in other words, what we're saying here, okay, let me just erase that, is that I want, if my input is this set of features here. Oops, my gosh. So I have F. So of course, note it's just an order, it's just this ordered set of the features. Again, until FP. Oops. I hope you understand that this is FP. Basta ka na muna na siya. The output should be, I think there's a way to overlay a text here. Nagidi. All right, so that's better. So the output should be, okay, should be this set F sub 1 prime, F sub 2 prime. Wala may sub din, so kanan na lang ako butaw. Dots, 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 F sub P prime. Such that F sub 1, let me just put it here. Okay. If I have a function P which measures the quality of the features, then the quality of F sub 1 should be better than or equal. I'll just call that Q, no, but a function that measures the quality, or you can think of, for example, the correlation of F1. You can think of information gain or any other metric, for example, any other measure, for example, that assesses the quality of the feature. So the quality of F1 should be the quality is better than the quality of F2 prime, so on and so forth. So meaning to say, what I'm doing is that I'm actually ranking the set of features. So I have F1, F2, FP. And what I do is to use a function Q to evaluate the quality of these features and then rank them from the best to the worst feature on the basis of that quality. So this process is called feature selection, and we've been doing papers on this. I think I have around 3 so far. I think one attendee here, Professor Lau, is a co-author. It's a consistent co-author of mine when it comes to feature selection. So that's what it does. If you want to read our paper on that, there's on someone else here. I think Professor Rojas is also here. He was also one of my co-authors, no, sa feature selection. So we did papers on this. Wait lang. Let me just remove this. All right. So that's basically what feature selection does. Now the other area of dimensionality reduction is called feature projection. Feature selection, what it does is wait lang. All right. Okay. Sorry for that. Yeah, nagbutan gid ko space dito to make some annotation. Sige. So what feature projection does is, unlike feature selection where you rank the features, you still have the same features. You're not transforming the features. You have the same features. You just want to find a ranking of the features. Feature projection is kind of different. So if I start with that feature set F again, wait lang. So this is F. So that's still my feature set. So I have F1, F2, dots, dots, dots until FP. What I want now is a different, it's a different feature set that combines these, the original features. So let's call that feature G. So G here would have G1, G2 until G sub K. So it's not necessarily the same dimension as your original features, but what it does is that your G1 might be a combination of the difference of F1 and F2 plus F3, for example, or 0.3 of F3, etc. But it's essentially what it does is that it combines the previous features. So G2 could be something like, I don't know, F1 times F2, etc. But a combination of that, of the features. So essentially what we're doing here, maybe FP, what we're doing here is that we're creating a new feature set on the basis of the original features. So we will see, that's why it's called projection, because we're projecting the data to another space, no? But we expect the projection to still have the same, to still kind of mimic the relationships that are in the original feature. So we just want to combine them. So this is also called as feature extraction, because we are extracting new features out of the original features. And what we're doing in manifold learning, most of the algorithms are really here on feature projection. So we're going to talk about this here in the next slides. Okay, so that's just the difference. In feature selection, we still have the same features. We're just ranking them. In feature projection, we're creating a new feature that basically embodies the original features. Okay, so see to the next slide. We're not going to talk about manifold learning. So manifold learning is basically most of the algorithms. In fact, I haven't seen one that does feature selection. But as far as I know, they are using feature projection, feature extraction. So manifold learning, so definitions first, this is also known as nonlinear dimensionality reduction. So we're going to briefly see a linear dimensionality reduction in a while, the principal component analysis in particular. But here, manifold learning is doing, it extends the concepts in PCA, for example, when it does linear dimensionality reduction to a nonlinear dimensionality reduction technique, which basically means that this is a set of techniques in machine learning aimed at discovering the low-dimensional structures, which we call manifolds, and we will define this later, embedded within the high-dimensional data. So a manifold is actually a concept in mathematics, so specifically in topology and differential geometry. So what happens is that this manifold is a topological space that is locally similar to Euclidean space. You will have a visualization or intuition of this, but think of it as basically just when we say topologically equivalent, we will define this later, as if I have a torus, for example, a donut, mathematicians would say that that's topologically equivalent to, for example, a mug of coffee, because you can transform one over the other without cutting or gluing something. We will see that later. But let's think of this manifold as basically just a space, a topological space that is locally similar to that Euclidean space. So this means that around every point in the manifold, there exists a neighborhood that is homeomorphic. So this means topologically equivalent to an open subset of the Euclidean space. There's a lot of terms here, so we're going to break them down in the next few slides. So first, what's a manifold? It's a topological space that, while potentially complex globally, actually appears flat or Euclidean when examined closely enough around any given point. So think about I don't know, the Earth, for example. No? So if you want to view the Earth globally for the outer space, you can see that it's really spherical, right? I don't think in a flat earther there is. So anyway, we know that at least science tells us that that's what it is. But if we go close enough, if we zoom in, Anania, we would notice that we're actually residing in a flat space or in a flat surface, right? Or Euclidean. So think of manifold as just that, as an intuition. Globally, it can be a complex shape, but if you view it from a local perspective, you zoom in, you would notice that it's not so different from a flat surface. Okay, so or Euclidean in that sense. So neighborhood just means that if I have a neighborhood of a point P in a manifold, so we know already what the manifold is, at least intuitively. This is a set of points surrounding P within a certain distance. So katong mga points nga naa sa yang neighbors niya. So yung neighborhood, so yung mga silingan in a way. So this is similar to how we might consider a small area around a location on a map. So homeomorphic, this is what we've said, topological equivalent, means that two spaces are said to be homeomorphic if there exists a continuous bijective function. So bijective function meaning you can just go from one over the other, no, so you have range and then back to the codomain and back to the domain. So in this case here, there's a bijective function. So I can go from one over the other. I can go back and forth, in other words, between them with a continuous inverse. So this means that they can be transformed into each other without tearing or gluing, so preserving their topological properties. So just like this mug of coffee and this torus here. So they have this joke we're no mathematicians, not a mathematician, but I've heard about this joke when I've read about mga papers on manifold learning, kind of community on manifold learning, is that it's just a joke. So they might find it difficult to distinguish between a torus and the mug of coffee because one can be transformed over the other without tearing and gluing. So it's just a joke amongst their community. So, and finally, we talk about an open subset of the Euclidean space. So when we talk about an open subset, we mean of the Euclidean space Rn. This is essentially a region without its boundary points. So for instance, an open disk, so just as I've demonstrated here, you have an open disk in R2, which includes all points inside the circle, but not the points in the circle itself. So this is a circle, this is a closed disk, and an open disk is basically the circle, but without including the points on the circle itself, so just those inside it. Okay, so this is an example of how of manifolds and charts, for example. So just think of what we're doing is we're basically just trying to put some patches around this torus and try to look in a way, when we go to that patch here, we think that it's no different, at least topologically, from the Euclidean space. It appears flat at those areas. So the thing with manifold learning, we're not going to go deeper into the mathematics here, but know that this manifold learning is actually based on those concepts. No, we just need to know what a manifold is or what it looks like visually. The algorithms themselves, if you want to use the algorithms, they don't really require that knowledge. But manifold learning is dependent on this hypothesis. It's called the manifold hypothesis. So the manifold hypothesis states that real-world high-dimensional data, such as images or sensor readings, lie on low-dimensional manifolds within the high-dimensional space. So this was the related to what we said a while ago about the blessing of non-uniformity. So and this manifold learning is based on this hypothesis. So this means that even though the data may have many features or dimensions, it can be effectively described by a smaller number of underlying variables or dimensions. Again, this is a hypothesis. So there are papers testing this hypothesis, but it's still a hypothesis at this point. So there's really no theoretical guarantee whether this is true in all cases. But I think it's a reasonable hypothesis to do now if you just look at images, for example. But there are papers testing this hypothesis. You can read on them if you want to. But what we're saying is that we think that even if real-world data are really highly complex, we still think that the real context about this data lie in the lower dimensional space that we want to learn, so that instead of learning the higher dimensional space, the original one, we can learn the lower dimensional representation of that data set. Okay, so in a more formal way of talking about it, the manifold hypothesis states this. So suppose we are given the data. So this is just the same data that we had, so xi, so from 1 to n. So you can still imagine that if each of these xi, but change the notation, but think of a data set that is n by d data set, so meaning d columns, capital D columns, and then you have n rows in that case. So here, the manifold hypothesis assumes that data are sampled from a distribution P that is supported on or close to a d-dimensional manifold M embedded in RD. So this is just a formal way of saying what we've said in the previous hypothesis, in the previous slide. So a manifold learning algorithm can then be thought of as a mapping F of xi, which lies in RD. So mean to say this is our original data set, which is d-dimensional, and it maps it to a new vector y, which is in this Rm. Okay, so now this M here is a lower dimensional representation of that higher dimensional space. And we call M here the embedding dimension, and it is usually much smaller than D, because of course, if you're just projecting in the same dimension, then you're not really doing dimensionality reduction. So what we want is to, instead of doing things at the higher dimensional space, we want to do it in a lower dimensional representation. So and we want to do it in this embedding space. So we call this M here as the embedding dimension. And this is usually much smaller than D, but could be higher than the intrinsic dimension. So there are two concepts here, the intrinsic dimension and the embedding dimension. The intrinsic dimension, think of it as the true dimension for what the lower dimensional representation of that higher dimensional data really is. But what we're doing with the embedding is that sometimes we might really get to that dimension. So we might get like a little bit higher than D. So think of D as just the minimum number of coordinates needed to represent the data accurately. So for example, if I would need, so if I have, say for example, 10 dimensions, but for this type of data, based on its intrinsic properties, we know that we would only need 3 coordinates or 3 axes to represent it. But the embedding dimension could be equal to that dimension or could even be higher. So for example, kung ato siya embed lang, mag-need ta og 5 instead of 3 dimensions, because we think that if we do 3 dimensions, it's not really, because our data could be noisy, for example, and there might be some other things that are that might not be, that would not allow us to really get to the true nga katong manifold that I mentioned. So sometimes we don't really get to that. So usually it's much higher, but it could even be equal to that. But just think of this D here as the minimum of that M. So it could be equal to D, but M could even be higher than that. Okay, so it's the minimum number of coordinates needed to represent the data accurately. So which reflects the true complexity of the data. So when P is supported exactly on M and the sample size approaches infinity, a valid manifold learning algorithm F should converge to a smooth embedding function. So wala sila distinguish there because we want the algorithm to converge to this mapping, to that embedding map, to that embedding function. Think of F as basically just this function that maps the higher dimensional data, higher dimensional space to that lower dimensional representation. So we want the algorithm to converge to that, so that if we have that, this would imply that the algorithm should be able to recover the manifold M regardless of the shape of M. So we have a way of getting back and forth if we project our data point. Because if we can't do that, then once we're already in the lower dimensional space, we cannot recover the original data. But we don't want that. We want to recover the original data so that we can measure something called a reconstruction error. Because if we want to project our data in a lower dimensional space, we also want to ensure that if we go back to the original space, our reconstruction is very close to what the original data looks like. Otherwise, we would have a data that is very different from the original data, right? A new data that's very different from the original data. So we don't want that to happen. So examples of manifold learning algorithms are kernel principal component analysis, local linear embedding, t-distributed stochastic neighbor embedding, Laplacian eigenmax, multidimensional scaling, MVUs, etc. And there are many more of these algorithms. So I'm just gonna run through here, although I'm gonna have a brief demonstration later of what these manifold learning algorithms do. So for example, you have here a Swiss roll. We call this the Swiss roll. So because it's like kind of bread bitong nakalukot, right? It's a Swiss roll. So what manifold algorithms do is that it tries to unfold this, no, to learn a lower dimensional representation of the Swiss roll. And think of the algorithm as basically unfolding this. What it does is that it starts from here, for example, or maybe here. And then if it walks through here, it knows that if I'm walking through here, because it thinks that this surface is flat, because of our assumptions later, it thinks that it's passing from this very red part and then nagkahayag siya until mabot siya sa blue. So inana yung button, it's unfolding it. And another one is this one. No? We'll see what these algorithms are doing. But this one is using, I think this uses or LLE, local linear embedding, now to unfold this Swiss roll. This one is using kernel PCA. So this is a different problem. What it does is you have 2 concentric circles here. You have the yellow circles within this purple circles. And then what it does is basically just separate these 2. So imagine that if you're walking through here, you don't get out of this yellow kind of your ring, right? So you would just be continually walking throughout here. And then you would realize that you're in the circle because you would go, if you put some starting position here, then you would know that you're always going back to the starting position. So that from the perspective of that ant or that point in that particular ring, so it will just look something like this. And kung naapo ko din here, it would look something like that. So what this algorithm does is basically, we'll see later, that projects it to higher dimensional space, and then when you revert back to the in the higher dimensional space, so that it's linearly separable there, and then when you go back to the lower dimensional space, you would see that the reduced space are already, the classifier will already learn that reduced space property. Okay, so another example is this. There are different kernels mga parameters. So if you vary the parameters, it would have this performance. Now, the thing with PCA, principal component analysis, I think some of you are familiar with this, but it's a linear dimensional reduction algorithm, is that if it reduces this, or it's not really reducing this if you notice, no. But if it transform this, it will still learn the same distribution all over again. So parihara ka man siya. If this is a circle, then it will still be a circle here. Maybe a different lang siyang view because what it's doing is just rotating that space. So if it has a different rotation, so muna na siya form. But kernel PCA, what it does is it separates these two. So it knows that this one it could be separated from this, so it separates them. Okay, so there are other examples where these manifold learning algorithms could really be used. For example, sa kaninga shape, if you use another algorithm like LLE, in any yang perspective, if it's another algorithm, it would be this. So I think the limitation ng sa manifold learning algorithm is that these embeddings that it learns are not really unique. No? So for example, if I use LLE, I might get a different lower dimensional projection compared to if I use, for example, t-SNE. And the thing with this is that in practice, what we do is we usually use a lot of these, many, not just one algorithm, but we try to see which ones are most likely reasonable based on some measurements. For example, some cluster quality for doing clustering, or classification performance if there are actual labels to that data set. So there's no one algorithm that beats the other one. So you would still have to use these other algorithms. So in tandem. Okay, so for the Swiss roll, kanisha, lahi po siya see, so kung LTSA yun ani, has an LLE, local linear embedding, kaya na yung view. If it's using LTSA, this is a manifold alignment. I think that's tangent alignment, and na yung perspective. And if it's different, like t-SNE, so in ani po siya. So in other words, the bottom line is that they have different projections to the lower dimensional space. But if you're interested only in understanding the contextual relationships at nila, then this would be sufficient. As long as ang problem lang is that if you're doing clustering and then you project your data to a lower dimensional space to cluster them there, and you're using t-SNE, for example, the actual distances might not really be that meaningful, because ang gibuhat na ni t-SNE is actually measuring the similarity to mga distances dito, and then the distances at the lower dimensional space might not really be cannot be interpreted in the same way as you would interpret it in the original space. So I think caution should be made when you do clustering using t-SNE, for example. So it's useful for visualization purposes, but if you do like you're really uncovering the structure of the clusters, no, from on that lower dimensional space, then it's something to be cautious about. Okay. Okay, so just a very brief nga ko lang, no. I thought that I had 2 hours to go on, but 130 minutes. So let's just briefly run through this. So before we talk about, I'm gonna focus on a single manifold learning algorithm, which is kernel PCA. But before we talk about kernel PCA, let's briefly talk about PCA. So to talk about this, let's consider this data set. This is the iris flower data set. So, and that data set has 3 classes, the setosa, versicolor, and virginica. And what we do is that we measure the petal width, petal length, sepal width, and sepal length of that flower. And your classes would be the type of flower, the species of the flower. So that could be the setosa, versicolor, or virginica. And what we do is that based on these features, we try to predict whether one is a setosa or one is a versicolor. Okay, so I have here a demo. Let me just show this. Let's change my screen. All right, so this is basically a 3D plot na of that data set. But notice nga, ang katong data set na to has 4 dimensions. So what I did is, to visualize it, is nag-pick ko sa katong first 3 dimensions, petal length, and sepal width. But I've embedded the petal width to the size of the scatter point. So meaning, kung gamay ang scatter point, like this one, it would have a low, mas gamay siya og sepal width in that petal width in that case. But if makadako siya, then it would have a large petal width. So inana lang siya para ma-view lang siya visually. So what we now do is, if we apply PCA to this, compute PCA here, what we're learning is that we're really trying to find, in a way, no, for intuition purposes, what we're doing is finding a new axis, defining a new axis to this data set that gives us the where the maximum variance are. So for example, kaning x-axis na to din here, this is where the maximum variance lies. Here, we could rotate that original space into this. But rotate, but just imagine na nindot siya pagkabutang, like tarong siya pagkaanan. So this red one would be the x-axis, the new x-axis, and then the yellow one would be the new y-axis. So what we're doing is that we're just finding a new coordinate system of this that gives us a new perspective of the data point, the data set. And then the advantage of this is that instead of viewing this in 3D, if I view it from this perspective here, I still see the relationships of the data points. Okay, so wait, something like that. No, so I really don't need the other dimensions to at least determine the class separation between the setosa versicolor and virginica, and to even know about the variances themselves. So I could just simply rotate this, and you can think of it as basically just finding these new axes. So for those who are more mathematically oriented, what we're doing here, and familiar with PCA, it's just an algorithm in linear algebra that what we do is basically find the eigenvectors and eigenvalues of the covariance matrix. So in a way, this first principal component, this x-axis here, represents the maximum variance. And this would be the percent explained variance ratio niya. So that's 73% in this case. So we're not going to delve into that. Kaya wala na ko time to do that, although I prepared a koan to delve deeper into that. But what we're doing here is that we're just taking all the eigenvalues ato niya from the original of the covariance matrix, and then we measured pila iyang percentage of the total eigenvalues. So that would be 73% in this case. And that's for the first principal component. And we can see that what PCA does is just this. So it's the same as rotating this original space, which was in 3D, to this new orientation. So in a way, we're just finding this new x-axis and new y-axis. So this is kasi rotate. By the way, I'm using plotly for this. So siya rotate. And we get something like this. So this still tells me how this class is different from this. So, but what it does is basically just rotating these and doing some linear transformations on it. So that's the limitation of PCA though. So the thing with those complex data sets, let me go back to my slide. Okay, for a while. Where is it? Okay. So the thing with high dimension with larger data sets is that they might not be if we use a linear transformation or we just use PCA, for example, they might not be able to capture some of the relationships. So sometimes unexplained variance, if you just use two principal components, would be much lower. So in that case, if I'm going to reconstruct it again, then I might not get to reconstruct it very near to what the original data are. So this is what motivates the manifold learning algorithms like katong ipang mention ito kanina. And we're going to talk about a specific algorithm here, which is kernel PCA. So kernel PCA is an extension of PCA, but it uses the techniques of kernel methods. So what's a kernel? A kernel function takes two input vectors and computes a similarity measure between them and returns a scalar value. So it is a function that computes the similarity between two data points in a potentially high dimensional feature space, without explicitly mapping the data into that space. So I'll explain this in a while. So think of the dot product, for example. So if you are familiar with linear algebra, you have two vectors and then you want to measure the dot product between them. It's a measure of similarity. So if they're orthogonal to one another, we know that the dot product would be 0 in that case. So meaning they're not similar, but if they're not, then they might be similar. So kana lang siya. But here in kernels, we're doing that in a higher dimensional space. So the purpose of kernel in kernel PCA is that it allows PCA to handle nonlinear relationships by transforming data into a higher dimensional space where linear separation is possible. Now, the question is, sir, you just mentioned that we want to project it to a lower dimensional space instead of the higher dimensional space, but why are we transforming it further to a higher dimensional space? Now, so let me just briefly demonstrate it here. The reason is that if you have so for example, na kayo mga data points here. Okay, so give me a little bit, a few seconds to do this on the iPad. So I'm just gonna do it in a few seconds. Okay, let me just set up this in a while. You can ask me questions at this point while I'm setting it up. I find it easier to do this there than to do it here on Keynote. Right. I think you can do it this way as well. For a while, just give me a little bit of time.
while Sir Daryl is drawing his examples, you may also chat your questions if there are any.
Yes. Yeah, I'd be happy to answer your questions. Yeah. Give me a few seconds. Sorry, taas siya. Murag ako prepare nga. 130 minutes today, Sir Nan. I thought 2 hours. Sorry. Pero medyo taas gid siya. If oops. So that it's it should not be this one. Wait lang. Do it again. Oh yeah, it works. Okay, so what I'm saying is that let's say for example that our data points are distributed this way. I have triangles here. Triangles. Ba't di ka drawing? So wait lang. Square na lang para sa yun. So square, 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 square. So this is just the same data atong circle atong data set before. And let's say for example that I have some circles here outside. Okay. The reason why we want to map this to a higher dimensional space first before we do dimensionality reduction is that here in this space, if we use a classifier, so our assumption here is that we're just using a linear classifier, meaning to say a classifier that basically just draws a line or a plane to separate these two classes. So for example, the classifier might go something like this. So if my classifier would decide that this is the decision boundary, it's still not going to make a very good classification because let's say, for example, it decides na kani siya class A. So correct siya in the class A because this is correctly classified. Okay, but there are 2 points here that are, no, sorry. But there are points here that are not correctly classified because if I say this is class A here and this is class B, then I would only have, if they are the same number, no, kung balance siya ng data set, then I would have at least 50% accuracy. That is if the same number of data points, because I've correctly classified the inner ring, but incorrectly classified these other parts here niya. Because that's just the power of, mura na ang ability in a linear classifier. It's only able to draw lines that separate them. And this is the case even if I do it this way, or if I do it that way. At some point, I would still be missing a lot sa akong accuracy if I do that. Now, the goal of kernels, of kernel methods in general is to learn this representation in a higher dimensional space first. So what I'm going to do is to map this. If I map this to a higher dimension, let's say, for example, 3D. So let's say anak na siya, no? It's possible nga at this space here, the squares would actually be dinhi, and then the circles are now below, okay? So something like that. And if that's the case, then my decision boundary could just be a plane that separates these two. So at the higher dimensional space, I am better at solving this problem. I'm better at linearly separating this this class here from this other class. So that's why we want to map it to a higher dimensional space. But again, the question is, which is a valid question, by the way, why is there a need to do that? Doesn't this defeat the very purpose of dimensional reduction? We want to reduce our data set, but now you're saying that we want to map it to higher dimension and then do the dimensionality reduction there. So I'm going to explain why that's important. The thing is, we have this trick. No, not a lot of things in machine learning are called tricks. So this is really important. This is an important trick. We call it the kernel trick. And the kernel trick tells us that even if we don't really need to perform these operations at a higher dimensional space, we just need to find a similarity of function, or a function that measures a similarity that kind of mimics what happens in the higher dimensional space. But in reality, what we're really doing, just computing things at the original space. So not really at the higher dimensional space. So it's just that that kernel function, by some equivalence, or by some by satisfying some properties, is really the same as operating at the higher dimensional space. So muna yung atong buhaton sa kernel trick later. So first, I'm going to do an example of how we map the higher dimensional space. Kadiyot na lang yun siya, Sir Nand. I think makaya rin ako in a few. Okay lang, extend gamay. So,
Go ahead, sir.
all right, thank you, sir. Sige. I hope you're not bored by my very long discussion. Sige lang, wait. Okay. Okay, so let's go back to this example here. So mapping to a higher dimensional space is basically just doing this one. So suppose that I have my original vectors uh, here. Now, so young components x1, x2, and x3. This is just the same as what we did before. The u is just u1, u2, up. But here, I'm not talking about a p-dimensional space. I'm just talking about the vector that resides in R3. So meaning three-dimensional lang siya. And what mapping to higher dimensional space means is that I need to have this function phi. We call this one the feature map, at least in the context of kernels. We call it the feature map. And this function phi basically maps this R3 to some, let's say, for example, R9, to a higher dimensional space. Or in general, if you have a p-dimensional vector there, then you're mapping it to Rm, where m is, wait, okay, of course, no, it should be at least as large as p. Because, of course, if it's not the case, then mura ra kag wala nag-map to feature space if it's even equal to that. But to account for that equality, I'm just gonna include that as well. But in general, that should be higher than that. And the thing with this mapping is that it could even be infinite dimensional. So we will see later now that we're actually using Hilbert spaces there. We will see that in the definition in a while. Okay, so what I'm doing is that I just want to map this from 3D to another dimension R9. So my mapping could look something like this. It could be x1, x2, x1, sorry, x1, 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 x2, x1, x3, x2, x1, x2, 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 x3, x3, x1, oops, x3, x2, x3, x3. Okay, now notice something here. It seems like I'm just arbitrarily doing this, but you will see later that if not, I add terms and it really corresponds to a specific kernel. But anyway, at this for now, just focus on what the function does and what this map does. It takes this three-dimensional vector, this nine-dimensional vector, because I would have 1, 2, 3, 4, 5, 6, 7, 8, 9 here. And that's just what it does. No, it just maps, it just takes this vector, which is in the lower dimensional space, to a higher dimensional space. And it doesn't even matter what these are here, at least for now. But we will see later that certain kernels would imply certain feature maps. So at least at this point, there's really, it is within the research literature for kernels to really find good kernels or suitable kernels for some problems. And they would correspond to some feature maps. But at this point, when we do kernel methods, it doesn't really matter no kung unsay naong ani niya. We don't even need to know what this looks like. What we really care about is the kernel function later, which we will see in a while. Okay, but that's just how mapping to a higher dimensional space looks like. We have a lower dimensional representation, and then we map that to a higher dimensional representation, which in this case could just be the products of the terms. Okay, so let me go back to my main slide. Right, so all right, so let's now talk about the kernel trick. We're almost there. So this technique enables efficient computation of the principal components by operating in the original input space while leveraging the properties of the kernel function. So the algorithm goes like this. And this is the procedure. The first step is to write the algorithm in terms of inner product. So we will see why this is the case. Inner product, because again, what we're doing is we want to measure the similarities, right? So if we do that, an inner product is just a generalization of the dot product that you know. So dot product, we'll briefly see that in a while. But just if you have two vectors, I just basically multiply component-wise ang katong imuhang elements mo vectors. If I have x1, x2, x3 for the vector x, and y1, y2, y3 for vector y, I just do x1 times y1, x2 times y2, y2 times x3 times y3. And then you add them. Okay. So we want to express them all as inner products. But of course, the dot product is not the only inner product. So here, we're generalizing it. That we have to first express all of the points in our data set as inner products. And what we do now is to create a mapping to assume that there is this mapping here that takes x to phi of x. So that's just the phi here was just the function that's just the mapping that takes me from the lower dimensional space to the higher dimensional space. And what it does is that it transforms x into phi of x, which lives in a higher dimensional space. And in fact, this can be infinite dimensional. That's why in the definition later, we are going to use a Hilbert space instead of the Euclidean space. And what we do next is to compute this k of xy here. This k of xy is called the kernel. So wala na ako na, di na siya capital letter, this should be a small letter because to be consistent with my notations, but that's okay. In some notations, they would use a capital K. In my case, I used a small letter K all throughout, but not ako siya change, but know that this is the kernel function. And this kernel function is just equal to the inner product of the phi of x and the phi of y. So meaning to say, if I transform all of my vectors in the original space to that feature space. So by the way, we call the higher dimensional representation as the feature space. So feature map minus phi, the space of that is the feature space. So if I am going to take the inner product of all of these vectors in the higher dimensional space, what I'm essentially doing is that if it satisfies some properties, it will be equal to this kernel. And what the kernel trick, the power of the kernel trick is that we don't need to compute this inner product at all. We just, if we find a suitable kernel that satisfies some properties, it's the same as computing this inner product. So in a way, we no longer need to know the actual form of this phi of x, or this phi of y here. We just need to compute k of xy. Okay, so example on the quadratic kernel. So abi na kog nag-kuan ko, mag-iPad ko na, but anyway, let me just briefly demonstrate that kasi nag-debug mo ato. Let's go back here. So for example, now if I have this original space, so I have my points here, so that would be x din here. I think much easier sa iPad. Sige, let me share that in a while. Edit lang gid kayo. I want to make sure that this is understood first before we go to the formalism. But this will be very quick. Few slides lang ni siya. Don't you worry. Dili ko mag-spend of 3 hours for this webinar. It's just that I thought that I would have 2 hours. So extend that a little bit if that's okay with you. So what's happening with phi, let's go back to that, is if I'm in this original space here, okay. Wait lang. And I have vectors x and y. So these are basically just points, right, in that space. And what I'm going to do is when I map this using phi, okay, so phi of, let's just phi of u to be general, no, hindi lang siya like specific to x and y because I've used x and y already. If I map this to a higher dimensional space, let's say 3D for now, what it's doing is that this one, what would be the best color? I think let's just use green. In this phi, in the feature space, this would now look not theta, but phi of x. Okay, so this is now the new point. But it's still that. It's just that it's a transformed version of that. And yeah, finish on y, in here, will just be here. But this would be your phi of y. Okay, so that's just what it's doing. And we're going to do this for all of the points in this original space. If I have another point here, if another point here, I'm going to have to map all of them to this feature space. So kanatong buhaton. Okay, so that's what the feature space is. And what we're doing is that if this represents a vector still, no? So let's say, for example, there's an arrow there, there's an arrow there. What the kernel trick is telling us is that this k of xy is a function that takes in the original x's and y's. So kanisha, it just takes in x, it just takes in y. And this is equivalent to just taking the inner product of your phi x and phi y. So in other words, what we're saying is that if I take the kernel of x, y in the original space, this is the same as measuring the similarity between them in the higher dimensional space. So this has a lot of implications because this means that we don't really need to do anything here in the higher dimensional space. We just need to find a kernel that does the same thing in the original space, and because they're equivalent, if some properties are satisfied. And now let's do the example. Example nato ganina. This one. Okay, so suppose we're given two vectors u and v. So again, that's u1, u2 until up because it's p-dimensional. And v here is v1, v2 to vp. And a feature map. Remember, the feature map is just a map, a function that takes u from the original space to a higher dimensional space. So muna siya to ang phi. So the phi here is now a little bit long because we're now dealing with a p-dimensional vector here. And that's just the same as what we did before. That's the pairwise of the components of the vector. So that's x1, x1. So for a general vector x, that would be x1, 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 x2. This is just what we did before until x1 to xp, and then x2, x1 to x2 to xp, xp to x1, and then until xp to xp. And then we add additional components here. We have additional components, the square root of 2c and x1 to the square root of 2c. Yeah, we multiply that to xp. And then another component called c. So this will correspond to a kernel later. And what we're going to do here is to show that if we take the inner product of this feature map here, conditional feature map, this is just equivalent to this kernel. And I argue that this one is a kernel. In fact, it is a kernel. We will see this one later. That's U transpose of V plus C. So the inner product that we're doing here is just the dot product, as you can see, because that's just the, this is just the dot product. So, and that makes sense because here, this is just in Euclidean space. So finite na siya nga space. So we don't really need to use unrelated products. So that's U transpose V plus C squared. So we're going to argue that when we take the inner product of this with this, it's just equivalent to this. Okay, so first is if we take the inner product of them, in fact, again, we're just using the dot product here. That's just equivalent to taking the element-wise product on nila. Okay, so that's just multiplying this with, I think I need to use another color. Let's use red. So taking this with this, and then you add them. So can I say equal, you add mo siya. And then this, you multiply this with this, and then you add them, so on and so forth, until you reach this. No, that's, oops, multiply that with that, and then you add them as well. You add the result. So that's just what we're doing when we take the dot product in this case. All right, so let me just delete that. Okay, wait lang. So if I take the dot product of the two, the inner product of the two, so in this case, just the dot product, then I get this expression here. So parehas akong gibuhat ganina nga. I just take this and that, then add, and multiply this with that, then add, etc., etc. I get this very long expression. That's U1 times U1 times V1 times V1 plus U1 times U2 times V1 times V2. So on and so forth until UP times UP times VP times VP plus 2 times C times U times sub 1 V1 plus etc. C squared. So na 2C na siya because again, we were dealing with square roots here. So if you multiply them, right, this will just be the square of that. So makancel siya. So that's 2C. And then you have U1 times V1. So that's why we have this expression. And finally, C times C, which would just be C squared. So again, gitranspose na ko siya daan because conventionally, we use the column matrix not to represent the vectors. But since di mo siya masud, ko ako siyang e-vertical. So that's why I'm taking the transpose here of that. Okay, so now what I'm going to do next is to find some pattern in this expression. I know that I can rearrange some terms here. So notice that this term, okay, so if throughout this kuan, kutob lang sa tadin here, for example, no, that nga part. Notice that there is a recurring term here. So all of them have a U1 and a V1. This also has a U1 and a V1 and a U1 and a V1. So what I can do is I can factor this U1 and V1 out since these are just products, right? And that's also the same here for the other terms. Since I didn't here put a recurring term is U2 and V2, and then I have U2 and V2. That is until to the P na sa katong pag multiply nimo. And that is also true here. Here our recurring theme nimo is UP and VP. Here you have UP and VP. And let's start with that last step. So I can rearrange this. What I'm going to do is to factor these recurring terms here to get something like this. Okay. Just erase that. All right. So I get something like this, that U1 times V1, and can we factor out the name, then it will be the sums of the U1, V1, U2, V2, etc. And what we end up with is a term which has these U1s and V1s, the recurring terms before, in front of these terms here. So that's U1, V1, then U2, V2 here, UP, VP, etc. And then can it would be the same, and then plus C squared. So what I can do now is I want to compactify this. This is a very dirty equation. So what I'm going to do is I'm going to simplify this because it's too cluttered. There's a lot of it. It's too verbose. So what we're going to do is we're going to compactify this using the summation notation. So this is just the sums from U1 times V1, etc., etc. This is just the same as taking the sum, there are P of them, from J equals 1 to P of the U sub J's times V sub J's, at least this one, right? And then we multiply that by U1, V1. The same thing happens with the other terms. We have U2 times V2 times the sum from J equals 1 to P of UJ sub times VJ. So on and so forth until UP times VP, and then the sum ng gapon siya, plus 2C and this plus C squared, okay? So what I'm going to do next now is to also notice another pattern emerging here. So notice that if I express everything as that sum here, I can also take out. So what I can do next is notice na kanisha is just the same as this. Just the same as that. Of course, no, the same po na siya din ha, but I'm not gonna, this is not ko siya hilabtan for now. I'm gonna focus on these parts here, these terms here. So what I'm gonna do is to factor these out as well, not to rearrange the terms. Okay, so that's what I'm gonna do. Sige, so we just erase that and move to the next slide. All right. So if I do that, then I get this refactoring niya, no? So that means that my U1s and V1s are now sums of their terms, and then ang kanisya, ako man siyang gi-factor out, gibutang lang ako siya sa right. Di ran ako siya gibutang sa right side ani niya nga term diri. And then the sums U1 kani U1 V1 U2 V2 UP VP is in this part kani siya part na. Okay, that part. Wala siya gamot. Anyway, that's it. So plus 2c times the sum of these plus c squared. Nakatawa na ko kamura siya gamot pag butang. So anyway, we have that. And what we're going to do now is to represent this as well in terms of a sum. Okay. So notice that this one can also be expressed as a sum. But I'm not going to use a j here. Okay. Multiply na ko siya ano niya, so that to avoid ambiguity. So I'm going to use a different index. But the index doesn't really matter. What matters is that if I'm going to expand this, I would get the same equation. So this one would just be ui times vi from I plus 1 to p. So it's just this one. And now I multiply this with the sum of uj times vj. And of course, this remains the same, 2c uj vj plus c squared. Okay, so what's going to happen now is if I'm going to, so what I'm going to do now is to remind you that the dot product of two vectors x, y, right? So that's x, I don't have a xy na lang, no, but just imagine a dot din ha. So just dot, no, kung latex nga format, that's just x dot y is equal to, is equal to x transpose times y. That would be the same, right? Not naman, because if I have, sige, let me just go back to just quickly lang, very, very quick. Go back to the iPad. So you can always ask me a question if you have a question. I'm setting this up. This will be very quick. Okay, so that's just the same, because if I have vectors here, u1, u2 until u sub p. Oops. Let's just consider a three-dimensional vector. So u3, and then I have v, v1, v2, v3. They are all column matrices, right? So you know that the dot product of uv is just u1, v1 plus u2, v2 plus u3, v3. So if I take the u transpose of v, that would mean I have u1, u2, u3, kaya transpose man na siya, right? And you multiply that by v1, v2, and v3. So you have a 1/3 matrix now because it's transpose, and 3/1, so you still get the scalar. So you just multiply this with that, this with this, and this with this, which is just the same as u1 v1 plus u2 v2 plus u3 v2. Okay, so that's just the point that I was making to get to my next line. Okay, so now we're almost there. So what I'm gonna do is to replace all these sums here with the matrix notation. So I'm gonna express them in terms of the matrix notation and get this. This would just be u transpose v. So you have u transpose v times u transpose v plus 2 times c u transpose v plus c squared. Okay, and notice that if I factor this out, this is just, the factor is just kani. That's just u transpose v plus c. You multiply that, so that's very clear now, because u transpose v times u transpose v, this will be this term, and then this one multiplied by this, you add this with this, that's just 2 times c u transpose v and c squared. In fact, we can really do this because the results here are just scalars. Wala na ko siya diretso, but this is just a scalar, right? This is a scalar, this is a scalar, so we can do that. And here, the result will be u transpose v plus c squared. And we've just shown that if we start with, if we can find a kernel, so in this case, we assume that this was a kernel, and in fact, it is a kernel. It's actually the same as taking the inner product of its feature map, so feature vectors niya, the vectors in the feature space, if you take the inner product of that, it's just the same as taking this kernel. So the essence of the kernel trick is basically leveraging that. So we need to find kernels where in which we need to find some functions, similarity functions in which assuming some properties would equal their inner products in that feature space. Okay, so and this is just an example, but there's a theorem that really guarantees that that would be the case if some properties are satisfied. We call this the Mercer's theorem, but this is actually originally in functional analysis, not in machine learning, but we're leveraging that here. That it states that if a function k, this was our kernel, that takes in x to a real number, because again, we're just measuring the similarity. If this function is symmetric and positive, in fact, positive semi-definite, what I'm trying to change, it can be expressed as an inner product in some possibly infinite dimensional feature space. This means that there exists a mapping such that this kernel is true. But I had something about a kernel trick. Basically, just saying that the kernel trick will be true. So here, this one is a Hilbert space, but just think of a Hilbert space as an infinite dimensional version of the Euclidean space, but you can do things like finding inner products there. So that's the thing that matters here, because the kernel trick doesn't really restrict you in with finite dimensional feature spaces. So that could even be infinite dimensional. So what are these properties here? We talk about symmetry first. This just means that if I take the kernel of x and y, so if I measure, so if I have two vectors here, so let's say, for example, that I have two vectors. This is x, and let's say that this is y. All right. So what it's saying is that if I start to measure my similarity from here, I don't want this color. Let's just use this. If I start from x to y, so and I call that one s, and that should be equal to the same distance, no, the same similarity, even if I start from y to x, I call that s prime. So in other words, what we're saying here is that this s and s prime, which I should be equal. And if that's the case, then it's a symmetric function. Okay, so meaning it doesn't matter where I start, x and y, they're symmetric. Okay, and that's the case for all vectors in our original space x. Okay, so this just means that between 2 points, between 2 points is the same. The similarity between 2 points is the same, regardless of the order in which they are compared. Okay, the next one is positive semi-definiteness. This just tells us that a function, if positive semi-definite, if for any finite set of points, we have these vectors x1 to xn in our original space x, and any real coefficient c1 to c2. If we evaluate this this equation here, evaluate the statement here, what we get is something that is not negative. So it's at least 0. And in fact, it's positive definite if we only account for the case na this would be 0 if the ci, cj's are 0. But if that's not the case, we're not doing that here because we just need a positive semi-definite gram matrix. So we will not add that restriction. So positive semi-definite lang need. So if we do this, we get a result that is not negative, or a non-negative result, so 0 or a positive value. So this property ensures that it ensures that the gram matrix, if you're again with linear algebra, the gram matrix, that's just your matrix of the your inner products, the similarities. So this ensures that that gram matrix K is positive semi-definite. And this is important because there are other properties, we're going to delve into them. We're not going to delve into them. So this is important because in kernel PCA, what we're really doing is, instead of computing the eigenvalues and eigenvectors on the covariance matrix, that's what we did with the PCA. Katong mag-iba, wala na ako show because of the lack of time. But here, instead of doing that on the covariance matrix, we're computing the eigenvalues and the eigenvectors on the kernel matrix, or the gram matrix, if you may. So it's important that we construct this gram matrix. So to construct this gram matrix, given these vectors, these p-dimensional vectors of x1, x2, xn, and you're given a kernel function k. Hindi ko pasabot na little k akong gigamit, but at one slide I used a capital K. I changed notation somehow the middle of preparing this slide, and I forgot to change that part. But we really refer to this little k, at least for the slide, as the kernel. But some presentations might use capital letter K. I just want to distinguish it from this matrix. So little k. So here, to construct that gram matrix or the kernel matrix, we simply take the kernel of x1 with itself, and so in other words, we take the kernel of all vectors with respect to all other vectors in our space. So we need to say, I take the kernel of x1 with itself. So that's this entry here. But in the next entry, that would be k of x1 and x2. I think you guys should turn on. Sige, let me write that again. So the next would be k of x1 and x2, so on and so forth. But on dots, it means that it's so on and so forth until you get x1 and xn. And that also holds true because this is just a symmetric matrix, but the property for kernel. This would just be the same. Kanisha would just be the same as this. So because of that symmetry. And so we just need to evaluate this, either the upper triangular matrix or the lower triangular matrix. Of course, the diagonals are also included there. And that's it. That's how you construct the gram matrix. An example would be, honestly, my example, but I think it's pretty clear how we do that. So the reason why we're so I did think example pa ta, but I think you get it, that if I have vectors here, wait, just briefly doing that example. I didn't think kayo. Sige, so let's go back to the iPad. It will be a very quick demonstration. Okay, so if we're given let's say two vectors here, okay, duha lang ka vectors per dili siya. And then they have negative actual values. So let's say 1, 0, I don't know, 2, and then V is 3, 1, 1. So to construct, so the kernel matrix here, since you only have two vectors, would be 2 by 2, right? So that would be k of x1 and x1, k of x2, x1 and x2, k of x2 and x1, and k of x2 and x2. So what you're gonna do is just measure using some kernel. So you can use the quadratic kernel, for example, which is just the quadratic kernel again. That's just if this is u and v, then that's just u transpose v plus some constant c squared. You basically just evaluate the dot product of the two. So that would be 1 times 3 plus 0 times 1 plus 2 times 1. That would be 3 plus 2, right? So that would be 5 plus some constant c, and then you take the square of that. It's my math doing right. 3 times 2, yes. 3, yeah, that's right. So, and then you put that here in the entry. So here that will be 5 plus c. So c could be anything. It could be 1, it could be 2. It could be anything. It's a hyperparameter that you can tweak with the kernel PCA. And you do that for all of the entries in this matrix. So that's just how we construct this kernel matrix. Okay, and we're almost there for the demo. So we're just gonna introduce a few kernels. So we mentioned that this algorithm is very dependent on kernels. So and there are a lot of kernels. And in fact, it's important because different types of kernels may have different shapes nilang ma-learn, different decision boundaries, for example, if you have a classifier. So the first is a linear kernel, that's just x transpose y, the dot product of them. And in fact, if we use this kernel, the kernel PCA is just equivalent to the standard PCA, if this is the kernel that we use. If you use another kernel, the polynomial kernel, the quadratic kernel that I mentioned before is a special case of that, but the polynomial kernel is the more general kernel. So in this case, it's an extension to the linear kernel to a polynomial of degree d, which allows for polynomial decision boundaries. So in this case, that would just be alpha times x transpose y plus c and d. And in fact, if you notice here, this is just if we use the quadratic kernel with an alpha equal to 1, then that would just be x transpose y plus c squared. And so that quadratic kernel is an example of this polynomial kernel. So this alpha is it should not be 0, because otherwise if 0 naman siya constant lang na din here. So you wouldn't be doing transformations or evaluating inner products in that case. So you need this to be positive. So this is a scaling factor, and C here is any constant term. In fact, if we use Python scikit-learn to perform kernel PCA, these are parameters that you can, hyperparameters that you can tweak, okay? So there's another one called the radial basis function. We sometimes refer to this as the Gaussian kernel, but I think it's more general than that because of the, we have some, wala ko nabutan diri, but in some cases, butangan like alpha. So this is widely used due to its ability to handle nonlinear relationships and its infinite dimensional feature space representation. In fact, this is what we meant. It's possible for your feature space to really be infinite dimensional. So, for example, if you use the radial basis kernel, it's easy to see that. Now, if you're familiar, if you remember your calculus, that if we take the infinite sum of those polynomial kernels, we actually get an exponential version of which is this one. So if you remember Taylor series, mga infinite sums ng mga Taylor series expansion niya. So you have your patong sums of polynomials, and then you get an exponential. Okay, so in this case, we get an infinite dimensional na kernel. So, but again, even if it's infinite dimensional, at the lower dimensional space, what really happens is that I'm just taking I'm just operating on the original vectors. I'm not really, at least not at our perspective, we're not really doing the explicit computation in the higher dimensional space. But because this is a kernel, we are guaranteed that this is the same as taking the inner products at the higher dimensional space. That's just what it means, okay? And we also have the Laplacian kernel, which is a variant of the RBF kernel, and it's just this one here. So instead of using the Euclidean distance or the Euclidean norm, it uses the Manhattan distance, so the city block distance. So you can think of the sum of the absolute values of x1 minus y1, x2 minus y2, etc., instead of taking the square root of the sum of squares. So that's just the Manhattan. You can review that if you're interested. So this uses the Manhattan distance. And then another one is the sigmoid kernel, which basically just maps this kernel to this x and y to a S-shaped na transformation. Okay, so and finally cosine similarity, and this is, I think, very common when we deal with texts. If, for example, in NLP, there are NLP researchers here. I think they're very familiar with this kernel. So the thing is, it measures it kind of, if there are a lot of words, for example, like dog, cat, there's another one as house, we would expect dog and cat to be very close because they're animals, so they're farther apart from a house, for example. At least not, depending on the context. So here, this is another kernel that you can use for that. So examples, hindi na natin ibutang, but to construct the matrix, you just use the gram matrix, and then ang entries niya ang kernel are the kernels of each of these vectors. No, pairwise nila x1, x1, x2, x1, x2, and x1, x3, etc. So now we go to the procedure. This is the final slide, and then the demo afterwards. We choose a kernel function. That's the first step, of course, linear, polynomial, Gaussian, RBF, Laplacian, etc. And then we construct the kernel matrix K. So that's K equals x1, x2, conditional matrix. And then finally, of course, now we first center the kernel matrix. That's important here, not to strip off the effect of the mean. So we want to center that. So to center that, we just evaluate this. We don't need to explain this, but what it's really doing is that if I'm going to perform these matrix operations, then this Z here is basically a centered kernel. And this 1 sub n, it's an n by n matrix with all elements equal to 1 over n. So we can see that we're just dividing. If you multiply that there, it's like taking the mean of that. So so all of the entries are 1 over n, and where am I? Oh yeah, n is the number of data points, and I here is the identity matrix. If you evaluate this, we get a centered matrix Z, kernel matrix Z. So the next step is now traditional PCA. We just find the eigenvectors and eigenvalues of this kernel matrix, and then the thing is, we still have to multiply each eigenvector by the square root of their respective eigenvalue to normalize the vector. And then the final step would be to select the top K principal components. If I want to just retain 2 dimensions, you just select the top 2 eigenvectors, meaning you're sorting them. In this case, you're sorting the eigenvectors according to the largest eigenvalues. So the first eigenvector should be the eigenvector with the largest eigenvalue, and then so on and so forth. And then that's it. No? So what I'm going to do now is to show a brief demo of how this works out. So imagine now ang niya kwato ni siyang perform manifold learning. So this is just the circles data set, the one that we showed before. A circle and then I compared kernel PCA with another manifold learning algorithm called T-distributed stochastic neighbor embedding. And then this is PCA. So of course, as expected, if we do PCA, we just get the same result, right? Because it's just a linear transformation. But if I standardize this, possibly marag mo, change na siya mga noun din ha. Okay, if I don't standardize, meaning you standardize the data. So meaning katong original mga data set mo siyang i-center putin mo siya daan. So you standardize that, you're basically stripping off the effect of that mean, and then of course the standard deviation would be 1. So in this case here, it's just like taking the z-score if you standardize, but it's at least for this problem, kay artificial mo siya nga data set, dili ka dagkog range, they're almost the same. There might be no need to standardize this. So some might not, it's not really a requirement to standardize this data set in that case. But if you're dealing with a data set with varying scales, so you might need to do that. So in this case, di ko mo standardize, kaya ganahan ko nga ma-reserve ni ang kaning circles din nilapita when we separate them. But notice what happens with kernel PCA. If I start with a low gamma here, remember that the gamma, 0.001, I restrict that. Remember that the gamma, this uses the radial basis function, so you can select various kernels here. But I'm using the radial basis function. Let's say the step size is 0.1. So if I start with a very low gamma, like 0.1, for example, notice that I just get a circle. It's very close to the principal component analysis because again, no, if i-load to mo gamma nimo, ang gamma reg effect ng katong RBF kernel, so more of like the standard PCA ra siya. But if I increase this, notice that it's really changing. Notice the movement here. Oops, hinay lang siya because I'm doing this. Okay. Sige, dito na lang po sa 1 para maklaro na to ang pa. So 1, and then if I increase this, notice the movement here. It's gonna go down. So move na siya down. In fact, at 1.3, wait, hihinay ko siya. At 1.3, oops, hihinay siya. Wait lang. All right. So let me go back a little bit before that. So at 1.3, it's still a circle, but I want to see the actual changes. So let's just use a step size of 0.01. Let's go back to 1.3. Notice that what happens is that if I continually increase this gamma, what the kernel PCA does is gradually moving or gradually separating them. So what pa siya effect 1.3, but notice nga ni-move na siya downwards. 1.34, it's moving downward. 1.35, it's moving downward. 1.36, again, it's moving downward. Mura siya hinay kay gamay kay resources gi-allocate ni Streamlit for this. So 1.37, it's gradually moving downward. At 1.38, what it does is that gawas na siya, right? But napay yung mga parts nga nag-intersect sila. But now at 1.39, what it's doing is really separating that these two classes. In fact, if I further increase this, ang circle niya kay mas squash siya, so it will just be like change it in how na siya straight line, so on and so forth. The lesson here for kernel PCA is that you really have to perform some experimentation to determine the best value of gamma. So you're gonna have to do some hyperparameter optimization, some cross-validation, for example, to really determine if this is the best gamma for that particular data set. So di ka pa na siya mawagtang. Okay, now let's move to the other. Balikon sa nako ang 1.30. Ay, sorry, kada ko sa gamma. Kung dako ka siya kay na-squash na po siya sa middle ang kaning ang katong oranges, and then muna yung forma sa gawa. So in fact, the choice of your gamma here really affects the quality of your reduction, of your transformation. So if I start with 1.30 and we visit the classifier performance here, so I'm just using a logistic regression to separate these two because I want to showcase the ability of kernel PCA to and manifold learning to separate non-linearly separable data sets. Of course, kung mo use a linear classifier like the logistic regression, line na mabuhat. So for PCA, it doesn't do really well. So these would be your performance metrics, the precision recall, score. Just think of them as the higher the value, the better. So in kernel PCA, kana siya, but if I increase this to 1.38, kung na itong part nga, ni-cross na siya din, increase imuhang performance here. In fact, 1.39. You're really completely separating them. And note that this is the testing data na ni siya. No? This is not the training data. So it's a test data. But for this problem, it's a very simple problem. So we would expect it to really separate them completely. Now, the other one is T-distributed stochastic neighbor embedding. So iyahang parameter is the perplexity. So if I start the perplexity 1, inana niya buhaton. So it's just going to compute the distances. But as I increase this perplexity here, mo change yung shapes, but no. Notice that it's changing the shape here. So on and so forth. Let's go to 25 na lang diretso, I guess. So not 25, 20 lang sa no. Like, what was siya separate good. So 20 na pa siya din ha, but if I increase the perplexity to 21, it's gonna start separating them. But in this case, in a form. And then if I increase that further, ang effect niya is na separate na niya in circles. So again, the classifier performance would be very good in that case. Na-compute pa siya din na. Let's do another example. The final example in this case would be on the moon's data set. So the moon's data set is muna siyang original nga data. Like just a concentric circles, because here your first class is here, your class 0 is here, class 1 is there. And then our goal is to let our classifier distinguish between the two classes again. So I'm gonna start with 0.1 na gamma gyapon din here, just to have the same na kuha niya. And then the perplexity would be 1, just so that we can see the effect of that. So what's happening is that for PCA, we don't expect it to really separate it well, because again, it's not going to, for non-linearly separable data sets, mura gina yung buhaton, embed niya, you get the same distribution because it's a linear transformation. So rotation naman ito yung gibuhat, right? In fact, we can see that if we standardize that here, ang buhaton ra ni PCA, oops, nilag siya, is to rotate that, no? So, but we're not gonna standardize. Okay, so lang gamay ka siya resources allocate, so hinay siya. And in fact, grabe ka computation gibuhat ang manifold learning, so you would really expect na mo hinay siya or mulag. Unfortunately. Okay, so experiment. I hope I did not standardize it. Kay Nicoan siya. Okay, that's good. Okay, so let's start with the kernel PCA. If I increase the gamma here, we would also notice that the kernel PCA, what it does is, oops, let's start with a bigger value na lang. Maybe 1. So let's start with a gamma of 1. Okay, hinay. Anyway, what it's gonna do is just to separate them. Hinay, oy, mani siya. It worked well yesterday when I tested this. Wait lang. Okay, good. So you can ask me a question if you already have a question right now while we're waiting for this. Na siya, problema lang siya. So let me just run this again. Let me just stop this and rerun this. Wait lang ha. If you have a question, then now's the best time to ask them while I'm doing the demo lang sa. I'd like to run this again. And nakuan siya. But berserk. Okay, so I'm back here. Pwede ko na to siya. All right. So we're gonna start with again with a larger gamma in this case. So some moons nga data set. And notice that if I start with 1.1, or a little bit larger na lang, like 10. And we use 2 components. So yeah, so what it's doing, so for example, kung 9 pa atong gamma, inani pa siya, no? Or maybe kung 1, I think kung 1 wala pa siya na separate yun. All right, or separated na siya, but let's try a lower value. So 0.5, for example, or maybe 0.1. At 0.1, it's still the same kind of moons, but when we increase this to like 4, it's gradually trying to separate them again. So inaani pa siya. But if we use a gamma of like 11, we can see that they're now really well separated. So kana siya. So for the perplexity, for t-SNE, if we increase this to 20, so at 1, kaya kana sa GM form. But if we increase this to 20, it's also well separated. So again, ang goal niya is that to find, if you do hyperparameter optimization, you can find the suitable hyperparameters here, perplexity, for example, to separate or to make your algorithm distinguish the classes better. Okay. All right. So I think that's it. No, wala ko na show katong one-dimensional case. I think that's all for my presentation. Well, ako lang itong i-show briefly when you ask questions, if you have questions about dimensionality reduction. That's all for my presentation. So thank you for listening. I'm now ready for your questions. If you have questions, you can ask me. I'd be happy to answer your questions.
Okay, thank you so much, Sir Daryl. I will give you a little bit of time before we will have the question and answer portion. I would like our participants to have their questions typed down at the Q&A box that we have in here. It's just at the bottom buttons over at the Zoom meeting interface. And I think this is one of the most complex complex seminar webinars that I'm able to host. However, I still had a lot to learn. Also, I had a lot of things to learn from you right now, Sir Daryl. And one is that manifold learning is actually one of the many ways you can reduce the dimensionality of a specific high dimension data set. In that there are it's actually a type of countermeasure for high dimension data. Am I right, Sir Daryl? And that
Yes.
one of the things that I also learned right now is that maybe this one is more of an enlightenment rather than previous learning. Artificial intelligence is actually made up of various categories or classifications, and most of them are just mimicking how humans think and work. And these various categories are being learned at different levels. And one of these is machine learning, where manifold learning is actually a subset. So this I learned that manifold learning is a technique, and it analyzes complex data coming from high dimensional data to find this low dimensional structure or feature maps. And using that, you can visualize the high dimensional data by revealing its shape. And this is what I actually learned from you teaching us about the kernel PCA. I think that's one of the part of the lecture that I was really listening into. And this is because there are data that you cannot easily put a boundary when it comes to decisions for classification, and you cannot use the usual PCA for that. And here comes using kernel, and that's what we are using at kernel PCA. And kernel PCA transform data into a specific higher dimensional feature space where PCA or other types of a boundary decision making can be made. And if the data is linearly inseparable, we can use kernel function to create a feature map where linear separation can be made. And you also said about Mercer's theorem, which is looking at two variables, which is symmetry as well as how do you call this? The positive semi-definiteness of a specific
Yeah, correct,
data.
correct.
Yes. And this is where I am I actually listened up here, and I saw with your visualization, it really enlightened me about it. And I think I want to learn I want to learn machine learning too later on. I'm actually not a mathematics or a computer science student. I'm actually a biology student. So this really holds a lot for me, especially that we are actually handling a lot of data for biological information. So we have bioinformatics for that. And one of the data that I was working on before was actually acoustic data. And we actually created some sort of categorization for the acoustic data, which includes harmonization or harmonics. And then we also have what you call as amplitude as well as intensity that we use to really formalize to create some sort of categorization of what family this particular bird came from. So I think with me learning about manifold learning or machine learning as a whole, it would be very helpful, no, to create an application perhaps, or a program perhaps that could help me identify the birds without even, looking at more variables by actually having machine learning. Now, manifold learning, I will just reiterate for those who are listening, manifold learning is a counter to the curse of dimensionality. Basically, manifold learning is one way that we use the non-uniformity of the data, then we can elevate that and create a more understandable data through the shape or the geometry. And I also learned a lot more about curse of dimensionality. I already understood this one before, but not in a machine learning idea. When we had our samples for the acoustic data that we had, I realized that the more features I put in, such as, for example, the distances between the acoustic data points, and also the features in which I would include other types of, let's say, for example, the noise, the levels or the volumes. If I add them, the data becomes more sparse because it adds more dimension to the data. And that is actually what you said about the curse of dimensionality, wherein the more dimensions you put in or the more features you put in, data can become more sparse, and the distances between the data points become too concentrated that they become insignificant. So yeah, and now I realized that I was enlightened about that it was actually the one happening when we were cleaning out our data before. So thank you so much, Sir Daryl, for
Yes.
all of
I'm
these.
actually quite envious. I'm quite envious that you discovered it during your research. Because from my end, I only knew about it when I reviewed the theory. I really wasn't able to see that in action though. Probably because I wasn't dealing with like in your case, mga real data set which really have large dimensions. In our case, we were dealing with that, but usually we don't, at least on my end, wala kay ko using distance matrix, or I probably because when I solve a problem, no, at least in machine learning, I already know about it. So I wouldn't go into exploring like katong pagkuhan sa mga distances. But I'm quite envious that you discovered it like on the spot, kind of a first-hand experience, no, with that sparsity in the data. But yes, I'm quite amazed that the theory really works. with that.
Yes, and now I'm also enlightened that this is how it should work. And later on, moving forward, it can be used as a new program for a new technology for in our field in biology for once. So thank you so much, Sir Daryl. For everyone who are listening here, you can actually ask your questions and put them in the Q&A box that we have here at the bottom corner of our Zoom interface. Or if you have any how do you call this one? If you have any insights that you want to tell Sir Daryl, you can put it in our chat box right now. As for me, I have a lot of insights. I was able to link my previous knowledge with that of Sir Daryl's lecture right now. And I was so happy to learn new things about machine learning, and especially in manifold learning, which is a very new idea to me. Okay, so thank you so much. How about our participants in the Zoom meeting right now? Do you have any questions or do you have any insights? You can type them up in our Q&A box or in our chat box. Okay, Sir Nan? Do you have Sir Nan around? Okay. Sir Nan, do you have any questions or do you have any insights to tell Sir Daryl right now? As for me, I already expressed it well.
Yes. But ako insight for myself. I
Sige,
wish I could
sir.
have I wish I could have limited the mathematical parts of it, no. So but unfortunately, for if you want to delve to machine learning, you've got to be prepared, no, sa katong mga of course, if you um to avoid barrier to learning, just want to apply machine learning, you don't really need to do the math that we just did a while ago, all those formalisms. There are packages like in Python, scikit-learn, PyTorch, TensorFlow, for example, con neural networks that you can just use. And I think a basic understanding of how matrices work is enough, no, and how probabilities work would be enough to use that, at least from the application side of things. But I think the focus would be more on properly interpreting the results. You don't really need to do those math. But if you want to go deeper into the theory, so ako, for one, I don't know, but my orientation as a person is more on the theoretical aspect of it. So it's just a personal thing. No, I don't think that I can understand the algorithm very well without looking at the mathematics behind it. So mutuin atong the way na ko pag-present. And I hope that it's also something na mo na learn, no? Because I think one thing that we can learn from that is we don't just blindly use these algorithms. Now I can use PCA, I can use kernel PCA. If we understand the theory behind it, we know when to use one over the other. So we become more clever users of the algorithm, because in machine learning, nothing really stops you in applying any algorithm to any data. But the problem there is, are we really applying this algorithm correctly for this type of data? So I would encourage, I know there are some people here who are interested also in the theory. I would encourage you to, if you want to explore machine learning, to start first with the application. If you're a person who's more comfortable with seeing things in action first before delving into the theory, you can do that. But you can also go the other way around, where you start with the theory and then you try to appreciate the application. So the books that I can recommend are The Elements of Statistical Learning. That's a very good book for someone who wants a more theoretical approach, a theoretical start for machine learning. But if you want a more applied approach, you can start with the Introduction to Statistical Learning. Same authors, but different perspectives in Nagbuhat. And there's also another one. I think data mining is a good entry point. It's data mining is a much easier entry point compared to machine learning. So you can also do that. I think the questions is Hernan, sir.
I think Sir Nad is already here.
Yeah. Sorry. I just had a class earlier. So actually, to be honest, I'm also into in terms of manifold learning, I'm also really into theoretical approach, since as what I know, the manifold learning, it's actually the reduction technique in the it assumes high dimensional data. So now, based on the discussions that you had, Sir Darrell, and also based on the enlightenment of Miss Jara, I also
Enlightenment.
yes, that's also what I also have that enlightenment right now. In terms of the manifold learning, it
We're
often
detect mga philosophical guru ani sir.
yes, yeah. Technically, ang face verification and recognition uses this one na di ay. Oh, 'di
True.
ba? Because technically, the manifold learning improves the performance of the learning models on task na gi-perform sa face
Mm.
verification and also recognition. O, 'di ba? Enlightenment po siya sa kuwang part. Okay,
The
now I
least
know.
I can think of it is a CT scan. Did you know?
Pwede
Yeah,
po siya.
because the CT scan uses a different, scales, no,
Mm.
in taking images, and therefore different features to be able to
Mm.
get the correct phase of the organ,
Yeah,
making it simpler.
yes, clustering,
Yeah.
classification, and all and such.
Mm.
O, 'di ba? O, 'di
Then
ba?
I was reminded with gram matrices because of the, getting the kernel and
Yeah,
determining
yeah.
its
Yeah,
Gram
similarity.
correct.
matrices.
Yes, correct. 'Di ba? That's highly computational na gid ni siya da. Okay.
Mm. Okay. So thank you so much for that, Sir Daryl. And of course, Sir Nan, he's actually having a class right now. Sir Nan, would you like me to
Hello.
do the certificate giving a little,
Yes,
or is
please.
it
Yes, please. Yes,
okay?
please.
Thank you so much. So because we don't have yet any questions, and we have a lot to talk about, and we already have a time limit right now, perhaps we can award the certificate, Miss Paula. And
Uh,
kindly take the YouTube streaming down.